Look up at the night sky. What do you see? A scattering of distant stars, perhaps the dusty band of the Milky Way. It seems peaceful, almost predictable. But what if I told you that this serene view is a grand illusion? That our universe, in its vast and ancient expanse, is filled with profound mysteries that defy all logic and challenge the very foundations of our understanding. Beyond the placid darkness, cosmic puzzles lurk in the void, and enigmas so baffling that they leave our most brilliant scientists grasping for answers, forced to question everything we think we know about the nature of reality itself. This is not the orderly cosmos we learned about in school. This is a frontier of the utterly unknown, a place where the rules of physics as we know them seem to bend, break, or simply vanish into the incomprehensible. For all our advanced technology and our deep-seated human drive to explore, we have only just begun to scratch the surface of the cosmos's deepest secrets. These aren't just small gaps in our knowledge, they are giant, yawning chasms in our comprehension. They are phenomena that suggest our universe might be far stranger, more complex, and more wonderfully bizarre than we ever dared to imagine. Today, we are embarking on a journey to explore 25 of these incredible cosmic puzzles. We will venture from the haunting silence between galaxies to the very fabric of space and time, confronting questions that have persisted for decades and discoveries so new they haven't even made it into the textbooks yet. This is a voyage to the very edge of human knowledge, a place where certainty ends and wonder truly begins. So prepare to have your perception of the cosmos completely reshaped. We are about to dive into a collection of unexplained phenomena that range from the ghostly whispers of dark matter to the terrifying power of cosmic explosions with no clear source, from structures so immense they shouldn't exist to voids of nothingness that stretch for hundreds of millions of light years. Each mystery we uncover is a piece of a grander puzzle, a clue that might one day lead us to a deeper truth about our place in this magnificent, bewildering universe. This journey is not just about listing strange facts, it's an invitation to share in the awe and the profound curiosity that drives us to look up at the stars and ask, what is really out there? Let's begin. Our journey into the cosmic unknown begins not in the far reaches of the void, but with a force acting upon us right here, right now. For decades, astronomers have known that our galaxy is not simply drifting aimlessly through space. It is on a journey moving at a staggering speed of over 2 million kilometers per hour. But the question was, where are we going? The ultimate destination of this epic voyage is what scientists have named the Great Attractor. Imagine a place in the cosmos with such an immense gravitational pull that it can draw in entire galaxies, including our own Milky Way, like moths to a flame. This mysterious point lies in the direction of the Centaurus supercluster, roughly 250 million light-years away. It's not a single object, but a gravitational focal point, a node in the cosmic web so dense and powerful that it dictates the motion of our entire local universe. The sheer scale of this influence is almost impossible to comprehend. It's orchestrating a grand, slow-motion dance of galaxies across hundreds of millions of light-years. Yet, for something with such a profound effect on our galactic neighborhood, studying the Great Attractor is like trying to identify a distant mountain while standing in a dense, foggy forest. The region of space where it resides falls directly behind the plane of our own Milky Way galaxy, in an area astronomers call the zone of avoidance. This is not a forbidden zone in a science fiction story, but a very real and frustrating observational blind spot. The central disk of our galaxy is thick with cosmic dust, gas, and the blinding light of billions of stars. This crowded region effectively creates a curtain that blocks our view of the universe beyond, obscuring the very anomaly we are trying to understand. For a long time, the Great Attractor was a ghost, its presence inferred only by the motion of the galaxies around us, its true nature hidden behind a veil of our own making. So what could possibly possess enough gravity to pull on thousands of galaxies? The leading theory points to a colossal concentration of dark matter, the invisible scaffolding of the universe that we can only detect through its gravitational effects. This theory suggests that the Great Attractor might be the heart of an unimaginably large knot of this mysterious substance, a gravitational anchor point in the cosmos. However, more recent observations from telescopes that can peer through the galactic dust using infrared and radio waves have revealed another layer to the mystery. It appears the Great Attractor itself might be just a waypoint on an even larger journey. The pull we feel may be due to an even more immense structure beyond it, known as the Shapley supercluster, a staggering collection of galaxies that represents one of the most massive concentrations of matter in the observable universe. This suggests we are being pulled not by one, but by a hierarchy of cosmic giants, each larger than the last. The Great Attractor, therefore, stands as a profound reminder of our limited perspective. It is both a destination and a signpost, a local mystery that hints at the far grander and more powerful forces sculpting the universe on the largest scales imaginable. But if the Great Attractor is evidence of a hidden force shaping the cosmos from the shadows, then the true architect of that structure is our next great cosmic mystery, dark matter. Think of everything you can see in the universe, every star, every planet, every swirling nebula. All of that familiar, luminous matter, the stuff that makes up you, me, and every galaxy we can photograph, accounts for less than 5% of the entire cosmos. The rest is unknown. About 27% of the universe is composed of this invisible substance we call dark matter. It does not emit, absorb, or reflect any light, making it completely undetectable to our telescopes. We cannot see it, but we know it is there because of its profound gravitational influence. It is the unseen skeleton upon which the visible universe is built. The first compelling clues emerged decades ago from the work of astronomer Vera Rubin. She was studying the rotation speeds of stars within spiral galaxies. According to the laws of gravity, stars on the outer edges of a spinning galaxy, far from the central mass, should orbit much more slowly than those near the center, just as Pluto orbits the Sun much more slowly than Mercury. What Rubin found, to her astonishment, was that this wasn't the case. Stars at the edge of a galaxy were orbiting just as fast as those near the core. The only plausible explanation was that the galaxies were embedded within enormous, massive halos of some unseen material. This invisible halo provides the extra gravitational glue needed to keep these fast-moving outer stars from being flung off into intergalactic space. Without dark matter, galaxies would simply fly apart. This gravitational signature extends far beyond individual galaxies. When we observe massive clusters of galaxies, we can see how their immense gravity bends the light from more distant objects behind them, an effect known as gravitational lensing. The amount of bending we see is far too great to be caused by the visible matter alone. There must be a tremendous amount of invisible mass within the cluster, creating a powerful lens that distorts our view. Furthermore, the way these galaxy clusters formed and evolved in the early universe only makes sense if dark matter was present to provide the initial gravitational seeds. It acts as a cosmic scaffolding, pulling ordinary matter together to form the vast structures we see today. So, what exactly is this ghostly substance? Theorists have proposed several candidates, each more exotic than the last. One leading contender is a class of particles known as WIMP, or weakly interacting massive particles. As the name suggests, these hypothetical particles would have mass and interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Another candidate is the Action, an extremely lightweight particle born out of theories trying to solve puzzles in particle physics. There are even more speculative ideas, such as the possibility that dark matter is made of primordial black holes formed in the first moments after the Big Bang. The global hunt to directly identify a dark matter particle is one of the most ambitious scientific endeavors of our time. Because these particles are so elusive, detectors must be incredibly sensitive and shielded from any interfering background signals. That is why experiments are located deep underground, in old mines or beneath mountains, where thousands of feet of rock block out cosmic rays. These laboratories operate in near-total silence, waiting for the telltale, minuscule bump or flash of light that would signal a dark matter particle weakly colliding with an atom in their detector. In space, observatories like the Fermi Gamma-Ray Telescope are searching for indirect evidence, scanning the skies for anomalous gamma-ray radiation that could be produced if dark matter particles were to annihilate each other when they collide. Despite these heroic efforts, dark matter remains at large. We are surrounded by it, passing through it every second, yet it continues to evade our grasp. This invisible cosmic majority is a humbling reminder of just how much of the universe remains hidden from our direct perception, a fundamental component of reality that we can only infer from its silent, gravitational shadow. Yet for all its profound mystery, dark matter is only part of the story of the missing universe. It is a cosmic placeholder, an invisible substance that provides the extra gravity needed to hold things together, but it doesn't act alone. In the late 1990s, two independent teams of astronomers were making meticulous observations of a very specific kind of stellar explosion, a Type 1 supernova. These cosmic events are crucial because they are standard candles. They always explode with roughly the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance with remarkable accuracy. What these researchers expected to find was that the expansion of the universe, set in motion by the Big Bang, was slowing down over time due to the collective gravitational pull of all the matter, both dark and visible, acting as a cosmic brake. They were stunned to discover the exact opposite. The most distant supernovae were fainter than their calculations predicted, meaning they were farther away than they should have been. The inescapable conclusion was that the expansion of the universe is not slowing down, it is speeding up. Some mysterious, repulsive force is overpowering gravity, pushing galaxies apart at an ever-increasing rate. This discovery was so revolutionary and counterintuitive that it earned the team the Nobel Prize in Physics in 2011, and it forced us to confront the existence of a force even more enigmatic than dark matter, dark energy. This dark energy is now understood to be the dominant component of our cosmos, making up a staggering 68% of the entire universe. Think of it this way: the familiar atoms that build stars, planets, and life account for less than 5%. Dark matter, the invisible cosmic scaffolding, makes up about 27%. The rest, the overwhelming majority of everything that is this mysterious energy infused within the fabric of space itself that is causing the cosmos to fly apart. The leading and simplest explanation for dark energy is a concept that Albert Einstein himself first proposed and then later famously discarded as his greatest blunder: the cosmological constant. This is not a substance in the traditional sense, but rather an intrinsic property of empty space. The idea is that even a perfect vacuum, a volume of space completely devoid of all matter and radiation, possesses its own inherent energy. According to this theory, as the universe expands and more space comes into existence, more of this vacuum energy is created, leading to a stronger and stronger repulsive force that drives the expansion to accelerate. It's a truly mind-bending concept. The nothingness of space is not truly empty, but is instead imbued with a dynamic energy that shapes the ultimate fate of everything. While the cosmological constant is the frontrunner in our models, other, more exotic possibilities exist. Some theorists propose a dynamic energy field nicknamed quintessence that permeates the cosmos. Unlike the steady cosmological constant, quintessence could change in strength and density over time, potentially even switching from a repulsive force to an attractive one in the distant future. Another, more radical idea is that our understanding of gravity itself is incomplete on the largest scales. Perhaps Einstein's theory of general relativity, which has passed every test thrown at it so far, needs to be modified when applied to the vast emptiness of intergalactic space. Each of these theories leads to a dramatically different future for our universe. If dark energy is indeed a constant force, as the cosmological constant suggests, then the most likely outcome is what cosmologists call the Big Freeze or heat death. In this scenario, the acceleration continues unabated. Over trillions of years, galaxies outside our local group will be pushed away from us so rapidly that their light will no longer be able to reach us, causing them to vanish from our observable universe. Individual galaxies will become isolated islands in an ever-darkening, expanding void. Stars will eventually burn out and matter itself will decay, leaving behind a cold, dilute, and lifeless cosmos, a quiet and dark end to all activity. There is, however, a far more violent alternative known as the Big Rip. This terrifying scenario could occur if the strength of dark energy increases over time. In this case, the repulsive force would not only push galaxies apart, but would eventually overcome all the forces that hold things together. First, galaxy clusters would be torn apart, then individual galaxies themselves. As the acceleration grows exponentially, the destructive force would reach into every solar system, tearing planets from their stars. In the final, cataclysmic moments, the force would rip apart stars and planets, and then atoms and nuclei themselves, shredding the very fabric of space-time until there is nothing left but a soup of disconnected fundamental particles. The universe would end not with a whimper but with a catastrophic, instantaneous tear. While current data slightly favors the more gradual Big Freeze, the true nature of dark energy remains one of the most pressing and profound questions in all of science. It is the force that controls the ultimate destiny of our cosmos, a silent, enigmatic pressure in the vacuum that is writing the final chapter of the universe's story, and we are only just beginning to learn how to read it. Moving from the vast, invisible forces shaping our universe to the fleeting, brilliant signals that flash across the cosmos, we encounter two of the most electrifying mysteries in modern astronomy. First, we have the enigma of fast radio bursts, or FRB. Imagine, for a single millisecond, a source in the distant universe releases more energy than our sun puts out over 3 entire days. This isn't the steady, predictable pulse of a pulsar. It's a cosmic scream, an incredibly powerful blast of radio waves that appears without warning, flashes into existence, and then vanishes just as quickly. When the first one was discovered in archived data in 2007, it was so bizarre and so brief that astronomers debated for years whether it was a mere glitch, an instrumental error. But then more were found. These bursts were real, and they were coming from far beyond our galaxy. The sheer intensity of these signals points to origins involving unimaginable energies, processes so violent they defy our everyday understanding of physics. What makes FRBs so captivating is their unpredictable nature. The majority of them are one-off events, a single, spectacular flash from a random point in the sky that is never heard from again. It's as if the universe is playing a game of cosmic whack-a-mole, with brilliant radio flashes popping off in the darkness. However, a crucial breakthrough came when astronomers discovered that some of these sources are repeaters. Unlike their one-time cousins, these FRBs fire off multiple bursts, sometimes in frantic, chaotic storms of activity, and other times in a more languid, sporadic pattern. This repetition was the key that unlocked a major part of the puzzle. By observing the same location on the sky, scientists were able to pinpoint the origin of one famous repeating burst to a specific galaxy located billions of light-years away. This confirmed that FRBs are not local oddities. They are extragalactic events, messengers from the deepest reaches of space and time. So what cosmic engine could possibly produce such a short, sharp, and fantastically energetic signal? The leading suspect for at least some of these bursts is a type of neutron star called a magnetar. A neutron star itself is the incredibly dense, collapsed core of a massive star, and a magnetar is a neutron star on steroids, possessing a magnetic field trillions of times more powerful than Earth. Theorists suggest that starquakes on the surface of a magnetar, or sudden, catastrophic rearrangements of its immense magnetic field, could release titanic amounts of energy in a flash, creating a fast radio burst. Other potential explanations involve the most dramatic events in the universe, such as the collision of two neutron stars or matter falling into a black hole. And yes, the possibility of an artificial source, a directed energy signal from an advanced technological civilization, has been seriously considered and widely discussed, though most scientists view this as the least likely explanation, given the immense energy required and the natural explanations that are steadily gaining evidence. The study of FRBs is a field moving at breakneck speed, with new telescopes and dedicated monitoring programs discovering them by the dozens, each one a new clue in our quest to understand these brilliant, mysterious cosmic transients. While fast radio bursts are a modern mystery, their story echoes a much older, and in some ways more haunting, signal from the cosmos. On a warm August evening in 1977, a radio telescope known as the Big Ear, operated by Ohio State University, was carrying out a systematic scan of the sky, listening for any sign of an artificial signal from beyond our world. The data was printed out on long sheets of paper, and a volunteer named Jerry Amon was reviewing the readouts a few days later. His eyes scanned across a column of letters and numbers, and then he saw it, a sequence of characters so unexpected, so perfectly aligned with what a potential alien signal might look like, that he circled it in red pen and wrote a single, now legendary word in the margin: wow. The signal was intense, and it was narrowband, meaning it was concentrated on one specific frequency, just as scientists predicted an engineered transmission would be. It lasted for a full 72 seconds, the exact duration the Big Ear telescope could observe a fixed point in the sky as the Earth rotated, rising to a peak and then fading away, painting a perfect curve on the printout. It came from the direction of the constellation Sagittarius, and it has never, ever been detected again. The WOW signal remains, decades later, the most compelling candidate for a potential artificial signal from an extraterrestrial intelligence in the history of the search for extraterrestrial intelligence, or SETI. Its credentials are impeccable. It was precisely the kind of signal researchers were looking for, appearing in a quiet part of the radio spectrum, a frequency that hydrogen atoms naturally emit, which was considered a logical watering hole for interstellar communication. The fact that it has never been replicated, despite numerous and extensive follow-up observations, is what turns it from a simple anomaly into a profound enigma. If it was a transmission from another civilization, was it a one-time beacon, a cosmic hello that swept past us and was gone? Could it have been an interception of a powerful, directed communication beam that was never intended for us, one that just happened to be pointed in our direction for that brief moment? Or was it, as skeptics argue, a signal from a passing human satellite or a piece of space debris that reflected a transmission from Earth, an explanation that, despite many attempts, has never been conclusively proven? The legacy of the WOW signal and the ongoing puzzle of fast radio bursts represent two sides of the same coin in our exploration of the cosmos. One is a solitary, perfect, and unresolved event from our recent past, a ghost in the machine that continues to inspire the search for other intelligences. The other is a whole new class of astrophysical phenomenon, a rapidly unfolding frontier of discovery that points to the existence of previously unknown and extraordinarily powerful natural processes. Together, they remind us that the universe is not only vast and strange, but also dynamic and transient, filled with brilliant flashes and elusive whispers on the radio waves that challenge us to listen more carefully, to watch more patiently, and to always be ready for the next great surprise. But the search for a single signal, whether natural or artificial, inevitably leads us to a much deeper and more profound question about the cosmos as a whole. If the universe is so vast and ancient, with hundreds of billions of stars in our galaxy alone, many of which are orbited by potentially habitable planets, then where is everybody? This is the essence of the Fermi Paradox, a puzzle that has haunted astronomers and philosophers for decades. The contradiction is stark. On one hand, the sheer numbers suggest that life, and even intelligent, tool-building civilizations, should be common. The ingredients for life are everywhere, and the universe has had over 13 billion years for such civilizations to arise and flourish. Statistically, the cosmos should be teeming with activity, a vibrant galactic community. And yet, when we listen, we are met with an eerie, profound silence. Our telescopes see no alien megastructures blocking the light of stars. Our radio antennas detect no clear, patterned greetings, and our planet has received no visitors. The sky is quiet, and this silence is one of the most unsettling mysteries we have ever confronted. One of the most compelling and admittedly sobering explanations is known as the Great Filter hypothesis. This idea suggests that there exists some kind of barrier, a nearly insurmountable challenge or a critical step in the evolution of life that prevents species from reaching the stage of interstellar travel and communication. The terrifying part of this theory is that we don't know if this filter is behind us or still ahead of us. If the filter is in our past, it means we are an incredibly rare fluke. Perhaps the jump from simple prokaryotic cells to complex eukaryotic life was a 1 in a trillion event. Or maybe the development of multicellular organisms or the rise of higher intelligence itself is the cosmic bottleneck. In this scenario, we are among the first, or even the only, species to have made it through this series of evolutionary gauntlets, which is why the galaxy seems so empty. The alternative is far more disquieting. What if the great filter lies in our future? This implies that the development of an advanced technological civilization inevitably leads to its own destruction. Perhaps once a species discovers the power of nuclear fission, genetic engineering, or artificial intelligence, it creates tools that ultimately lead to its extinction. The silence of the cosmos, in this view, is a graveyard of civilizations that failed to pass their final test, a warning we would do well to heed. A much less ominous, though equally mind-bending, possibility is the zoo hypothesis. Imagine our Earth as a vast, designated wilderness area within a galactic nature preserve. The idea is that advanced extraterrestrial civilizations are aware of us, but have chosen a strict policy of non-interference. They are observing us from a distance, allowing our culture and civilization to develop naturally, without outside influence, much like anthropologists studying an uncontacted tribe in the Amazon. This would explain the lack of direct contact. They are waiting for us to reach a certain level of maturity, perhaps a technological or ethical milestone, before initiating first contact. Another variation on this theme is the planetarium hypothesis, which proposes that our entire observable universe is a sophisticated illusion, a projection created by a hyper-advanced intelligence to appear empty and uncharted. While these ideas venture into the realm of pure speculation, they highlight a crucial point. A civilization millions of years more advanced than ours would possess capabilities and motivations that we might not even be able to comprehend, making their actions or lack thereof fundamentally unpredictable. Then there is the simple, humbling argument of scale. Space is almost incomprehensibly vast. The distances between stars are so enormous that even if the galaxy were brimming with life, the chances of two civilizations existing at the same time in the same galactic neighborhood and being technologically compatible for communication are astronomically low. Consider this, our own radio signals have only been leaking into space for about a century, creating a tiny bubble of human-generated noise barely 100 light-years across. In the context of a galaxy that is over 100,000 light-years wide, our announcement of "we are here" is little more than a faint whisper in a colossal, echoing cathedral. Furthermore, an alien civilization might be using communication technologies we haven't even dreamed of: neutrino messaging, quantum entanglement, or something beyond our current physics, making their signals completely invisible to our current detectors. They could be chatting all around us, and we would be none the wiser, like a person in the middle of a bustling city who is deaf to the radio waves carrying all the cell phone calls. The problem may not be that the universe is empty, but that it is simply too big and our time within it too fleeting to have found anyone else yet. The Fermi Paradox forces us to confront our own cosmic significance or insignificance. It is a mirror reflecting our deepest hopes for companionship in the void and our deepest fears of being utterly alone. Now, let's shift our focus from the grand question of cosmic loneliness to a crackle of static that holds the blueprint of the entire universe. This is the cosmic microwave background, or CMB, the oldest light we can see. It's the faint, leftover heat from the Big Bang itself, a snapshot of the infant cosmos when it was just 380,000 years old. For decades, this cosmic fossil has been a cornerstone of modern cosmology, confirming that the universe is, on the largest scales, remarkably uniform and isotropic. This means it should look the same in every direction, with no preferred axis or special center. But then, scientists found something odd, something that seems to challenge this fundamental principle. They called it the axis of evil. This name isn't just dramatic flair, it reflects just how troubling this discovery is to our standard models. When researchers meticulously analyzed the subtle temperature fluctuations in the CMB, the tiny hot and cold spots that are the seeds of all future galaxies, they noticed a bizarre and unexpected pattern. These fluctuations aren't completely random. They appear to be subtly aligned or correlated with the plane of our own solar system and the direction of the Earth's motion through space. In a universe that is supposed to have no center and no special direction, finding that the very first light of creation seems to be oriented around us is, to put it mildly, deeply unsettling. It's as if you were studying a vast, ancient forest and discovered that all the oldest trees had grown in a pattern that perfectly mirrored the layout of your own backyard. The correlation is so unexpected that it suggests either a profound flaw in our understanding or a cosmic coincidence of staggering proportions. So, what could possibly explain this eerie alignment? Cosmologists have put forward several possibilities, each with its own implications. The first and most comforting explanation is that this is simply a colossal statistical fluke. When you have a massive dataset like the CMB map, you might occasionally find patterns that look significant purely by chance. It's like finding a face in the clouds. The pattern isn't really there, it's just how our brains interpret random noise. Scientists have run countless simulations, and while the axis of evil is a rare outlier, it's not completely impossible for randomness to produce it. Another strong possibility is that this is not a feature of the universe at all, but an artifact of our measurement. Something in our local environment might be contaminating the signal. Perhaps dust within our own solar system, or even the way our spacecraft gathers data, is imprinting this specific pattern onto the CMB map, creating an illusion of a cosmic axis where none truly exists. However, if it turns out to be real, the implications are revolutionary. It could mean that the universe is not perfectly isotropic after all. There might be a preferred direction on the largest scales, a fundamental lopsidedness to the cosmos that would force us to rewrite the textbooks. Some theorists have even proposed that this alignment could be a cosmic bruise, a scar from a time before the Big Bang. It might be evidence that our universe collided with another universe in a vast multiverse, an event that imprinted a direction onto the fabric of space-time. Or it could point to the influence of something else entirely, a mysterious energy field or a property of dark energy that breaks the symmetry of space itself. The axis of evil remains one of the most persistent and controversial anomalies in cosmology. It's a ghost in the machine of our deepest cosmic map, a whisper that the universe might be even stranger and more structured than we ever imagined, and that our place within it, for now, remains a profound and beautiful mystery. Sometimes the most baffling cosmic mysteries are not found in the distant depths of space, but are instead discovered much closer to home, in the subtle, unexpected behavior of our own robotic explorers. This brings us to the curious case of the Pioneer anomaly. Launched in the early 1970s, the Pioneer 10 and Pioneer 11 spacecraft were true trailblazers. After completing their primary missions to Jupiter and Saturn, they continued on their trajectories, becoming the first human-made objects destined to leave our solar system. For decades, NASA scientists meticulously tracked their paths, using the precise Doppler shift of their radio signals to monitor their velocity. And that's when they noticed something was off. Both spacecraft were experiencing a tiny but persistent and unexplained deceleration. It was as if an invisible hand was gently but constantly applying the brakes. This minuscule drag was equivalent to just 10 billionths of the gravity we feel on Earth's surface, but over millions of miles, that tiny effect added up, putting the probes about 240 miles off their predicted courses. For a community of scientists who rely on the absolute predictability of physics, this was a major red flag. Naturally, the first and most thrilling suspicion was that Pioneer had stumbled upon something profound. Perhaps it was the first tangible evidence of a flaw in Einstein's theory of general relativity. Or maybe the spacecraft were plowing through a local concentration of dark matter in our solar system, whose gravitational pull was tugging them backward. Others proposed more exotic ideas, like the influence of extra dimensions or new properties of gravity that only became apparent over vast interstellar distances. For nearly 2 decades, the Pioneer anomaly was a celebrated puzzle, a potential crack in the foundation of modern physics that had theorists working feverishly to find an explanation that would rewrite the rules of the cosmos. It was a classic detective story, with the entire solar system as the crime scene and the laws of physics themselves as the prime suspect. The turning point in this decades-long mystery, however, came not from a revolutionary new theory, but from painstaking, meticulous forensic work. A dedicated team of researchers embarked on a monumental effort to recover old data files, including early design documents, engineering telemetry, and even notes scribbled on punch cards that had been stored in someone's garage. They used this data to create an incredibly detailed computer model of the Pioneer spacecraft, accounting for every conceivable force acting upon it. They modeled the gentle push of the solar wind, the minuscule gravitational tugs of all the planets, and even the tiny particles of dust in interplanetary space. But the real breakthrough came when they focused on the spacecraft's own heat. The Pioneers were powered by radioactive thermoelectric generators, which produced a significant amount of waste heat. The team realized that this heat wasn't radiating away from the spacecraft symmetrically. More of it was being emitted from the back of the dish-shaped main antenna, which was pointed toward Earth, than from the front. This created a tiny but constant recoil force. Just like a faint, ethereal engine, the spacecraft's own thermal radiation was giving them a tiny push backward, exactly matching the observed anomalous deceleration. The resolution of the Pioneer anomaly is a powerful lesson in scientific humility. It shows us that the universe doesn't always need dark matter or new physics to throw us a curveball. Sometimes the answer is hiding in the plain sight of engineering details we initially overlook. It's a testament to the importance of considering all possibilities, no matter how mundane they may seem. This case highlights a fundamental principle of the scientific process. the relentless pursuit of an answer, even when that answer turns out to be less glamorous than we had hoped. It serves as a crucial reminder that before we invoke the truly exotic to explain an observation, we must first exhaust every effort to see if the mystery can be solved with the tools and understanding we already possess. The universe is strange enough, but its strangeness is often woven into the most ordinary of details. Now, as we turn our attention from the subtle forces acting on our own spacecraft to the distant light of other suns, we encounter a star that has become a modern icon of cosmic mystery. Nestled in the constellation Cygnus, about 1,460 light-years away, lies a seemingly ordinary star named KSE 8462852, but you likely know it by its more popular name, Tabby's star, named after the astronomer Tabitha Boyajian, who led the team that first studied its bizarre behavior in depth. What makes this star so special? The Kepler Space Telescope, designed to hunt for planets by detecting the tiny, periodic dips in starlight they cause as they transit, found something around this star that defied all expectations. Instead of the gentle, predictable dimming of a planet passing by every few days or weeks, Kepler observed dramatic, chaotic, and completely irregular drops in brightness. These weren't the slight dimmings of 1 or 2% caused by a Jupiter-sized world. These were staggering plunges. At one point, the star's light output dropped by a staggering 22%. That's like having a fleet of objects so enormous they blocked out nearly a quarter of the star's light. Nothing in our standard cosmic playbook could explain this. The hunt for an explanation began, and the theories proposed were as wild as the data itself. The initial natural explanation pointed to a massive swarm of comets. Perhaps a family of icy bodies shattered by a collision was creating a vast, uneven cloud of dust and debris orbiting the star. As this clumpy swarm passed in front of the star, it could, in theory, cause the bizarre, irregular dimming patterns. It was a plausible idea, but it had problems. To block that much light, you would need an almost unimaginable number of comets. We're talking hundreds of thousands, if not millions of them. The scale required pushed the limits of what we believe is possible for a single solar system. This is when the most tantalizing and famous theory emerged, the idea of alien megastructures. Astronomer Freeman Dyson had once speculated that a sufficiently advanced civilization would eventually need to harness nearly all the energy from its home star. To do this, they might construct a vast array of orbiting solar collectors, a concept now known as a Dyson sphere. What if, the thinking went, we were not seeing a natural debris cloud, but the partially constructed framework of such a sphere? The irregular, block-shaped dips in light could be caused by massive, artificial panels or collectors arranged in a complex and incomplete swarm passing in front of the star. It was a breathtaking proposition, the potential first evidence of intelligence operating on a literally astronomical scale. Of course, the scientific community did not simply accept this extraordinary idea at face value. A global effort was launched to study Tabby's star across the entire electromagnetic spectrum. If there was a construction project of that magnitude underway, it should be generating a lot of waste heat. All that absorbed stellar energy would have to be re-radiated as infrared radiation. Scientists pointed every available telescope, from the infrared-sensitive Spitzer Space Telescope to giant radio antennas, toward the star, searching for this telltale thermal signature or any artificial radio signals. The results, however, were disappointing for those hoping for aliens. No excess infrared heat was found. The star's energy budget seemed normal. It wasn't being absorbed and re-radiated by a vast shell of machinery. Furthermore, subsequent studies revealed another strange clue. Long-term observations of historical photographic plates showed that Tabby's star had also been gradually dimming over the past century by a significant amount. This long-term fading, combined with the short-term dips, made the comet swarm theory even less tenable and deepened the overall mystery. So where does that leave us today? The alien megastructure hypothesis, while never the favored explanation among most astronomers, has been largely set aside due to the lack of supporting evidence. The focus has shifted back to more complex natural phenomena. One leading theory now involves dust, lots of it. Detailed follow-up observations showed that the different colors of light from Tabby's star were being dimmed by different amounts. Blue light was blocked less than red light. This is a classic signature of dust where smaller particles scatter blue light more effectively. This suggests that whatever is passing in front of the star is not solid and opaque like a planet or a solid megastructure, but is made of fine, diffuse material. The current best guess is that the star is surrounded by a massive, clumpy, and dynamic ring of dusty debris, possibly the result of a catastrophically destroyed planet or a series of colossal moon collisions. The irregular dips could be caused by giant clouds of fine dust and planetary fragments on eccentric orbits, casting their tangled shadows toward Earth. Tabby's star stands as a powerful reminder that nature is often more inventive than our wildest science fiction. It forces us to question our assumptions, to consider the truly extreme events that can shape solar systems, and to continue looking up, always wondering what other strange and wonderful secrets the stars are keeping. Just when you thought the universe couldn't get any more mysterious with its dark matter and dark energy, it turns out we have a problem with the regular stuff too. The ordinary matter you and I are made of the protons and neutrons that form atoms, which scientists call baryonic matter, has also gone missing in a truly cosmic game of hide and seek. Based on our most precise measurements of the early universe, specifically from the cosmic microwave background, we have a very good ledger of how much of this normal matter should have been created in the Big Bang. Yet when astronomers take a full inventory of everything we can see today, all the stars, all the glowing gas clouds, all the planets, they come up staggeringly short. Nearly half of all the atoms that should be out there are simply unaccounted for. It's as if we built a universe from a precise recipe, but when we go to serve the meal, half the ingredients have vanished from the kitchen. So, where could an entire universe's worth of atoms be hiding? The leading suspect isn't some exotic new form of matter, but rather a state of matter so diffuse and elusive that it has evaded our detection for decades. Theorists call it the warm-hot intergalactic medium, or WIM for short. Picture the grand structure of the cosmos not as a collection of isolated islands, but as a single, vast spider's web. Galaxies and galaxy clusters are the dense knots where the silk is thickest. The WIM is believed to be the incredibly tenuous filaments of gas that stretch between these knots, forming the cosmic web itself. This isn't cold, dense gas that easily forms stars. It is a superheated plasma, warmed to temperatures between 100,000 and 10 million degrees by the gravitational shock waves from collapsing galaxy clusters and the ferocious outbursts from supermassive black holes. At these tremendous temperatures, the gas is so ionized, stripped of its electrons, that it doesn't emit light in a way our traditional telescopes can easily pick up. It's a ghostly, seething ocean filling the voids of intergalactic space. Detecting this faint, hot whisper of a signal is one of the most formidable challenges in modern observational astronomy. You can't just point a regular optical telescope at a seemingly empty patch of sky and see it. The WIM is virtually transparent. Instead, astronomers have had to become cosmic detectives, using indirect and incredibly clever methods to find its signature. One of the most successful techniques involves using distant beacons known as quasars. These are the intensely bright cores of active galaxies, powered by voracious supermassive black holes. As the brilliant light from a quasar travels billions of light years to reach us, it passes through these invisible filaments of the WIM. The hot gas in the filaments doesn't block the light entirely, but it does absorb very specific wavelengths, imprinting a unique barcode of absorption lines onto the quasar's spectrum. It's like looking at a distant, brilliant lighthouse through a faint, hot fog. By analyzing the specific patterns of dimming in the quasar's light, scientists can deduce the composition, temperature, and density of the invisible fog itself. This is painstaking work requiring the most sensitive space-based observatories like the Hubble Space Telescope and the XMM Newton Telescope to gather enough of these fragile clues. The hunt for these missing baryons is more than just an exercise in cosmic accounting. It's crucial for completing our picture of how the universe evolved. This warm hot gas is the logical resting place for a huge portion of the universe's normal matter. After the Big Bang, the primordial hydrogen and helium were spread almost perfectly evenly. As gravity began to work its magic over billions of years, it pulled this material into the great cosmic web we see today. The WIM is the predicted repository for all the matter that was pulled into the filaments but didn't quite make it all the way into the dense galaxies. Finding it confirms our models of cosmic structure formation. Recent years have seen major breakthroughs, with astronomers finally claiming to have found strong evidence for a large portion of the missing matter exactly where the WIM models predicted it would be, woven between the galaxies. This discovery closes a major chapter in cosmology, assuring us that the atoms are, in fact, all present and accounted for. They were just hiding in plain sight, in the most desolate and enormous spaces between everything else, completing the invisible architecture of our universe. But as we grapple with the missing pieces of our cosmic inventory, we must now confront a paradox that strikes at the very heart of our understanding of reality, a puzzle born from the most extreme objects in the universe, black holes. This is the black hole information paradox, and it isn't just a quirky thought experiment. It represents a fundamental clash between the two most successful theories in all of physics: Einstein's general relativity and quantum mechanics. General relativity describes gravity as the curvature of spacetime by matter and energy, and it predicts that a black hole's boundary, its event horizon, is a point of no return. Once anything, a particle, a spaceship, or an entire encyclopedia of information crosses that threshold, it is lost forever to the outside universe. The black hole, according to this theory, is defined by only three simple properties: its mass, its electric charge, and its spin. It doesn't matter if you throw in a perfectly sculpted diamond or a truckload of burning garbage. The black hole will consume it all and reveal nothing about what it ate. It is, in the parlance of physics, the ultimate shredder. Now enter quantum mechanics. This theory governs the bizarre world of the very small, and it has a sacred, unbreakable rule: information cannot be truly destroyed. Information, in this context, means the specific quantum state of every particle, its position, its momentum, its spin. The principle of unitarity dictates that this information must be preserved. If you could somehow track every single particle and its state, you should, in theory, be able to reverse time and see exactly where everything came from. It's the ultimate cosmic ledger, and the books must always balance. For decades, physicists assumed this wasn't a problem. They thought the information that fell into a black hole was simply locked away inside, trapped forever behind the event horizon. It was lost to us, but it still existed somewhere in the universe, so the quantum rule wasn't technically broken. That was the comfortable consensus until Stephen Hawking stepped in and turned everything upside down. Hawking made the revolutionary discovery that black holes are not completely black. Due to weird quantum effects occurring right at the edge of the event horizon, black holes slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. This radiation, however, is purely thermal. It's random, featureless heat, like the glow from a hot stove. It carries no information whatsoever about what fell into the black hole. And here lies the core of the paradox. As the black hole radiates, it loses mass and eventually evaporates completely, vanishing from existence. When it's gone, all that remains is this random thermal radiation. So, what happened to the information that made up the diamond and the burning garbage? According to Hawking's original calculation, it has been irretrievably erased from the universe. The cosmic ledger has been set on fire. This presents physics with an impossible choice. Either general relativity is wrong and information can escape a black hole, or quantum mechanics is wrong and information can be destroyed. Both options are catastrophic for our current understanding of the laws of nature. The search for a resolution has driven theoretical physics into some of the most mind-bending territories it has ever explored. One of the most profound ideas to emerge is the holographic principle. This concept suggests that all the information contained within a volume of space, like the interior of a black hole, can actually be encoded on its boundary, its event horizon, much like a three-dimensional image is encoded on a flat, two-dimensional hologram. In this stunning picture, when an object falls into a black hole, its information isn't actually transported inside. Instead, it is scrambled and imprinted onto the event horizon itself. Then, as Hawking radiation is emitted, it subtly carries this encoded information away like a slow, careful data transmission. The information was never truly lost. It was just translated into a form we couldn't initially recognize. This principle radically redefines our notion of reality, implying that the three-dimensional world we experience might be a projection from a two-dimensional surface at the edge of the universe. Another compelling proposal is known as black hole complementarity, an idea championed by physicists like Leonard Susskind. This principle tries to resolve the paradox by asserting that there is no single objective truth about what happens to information. It proposes that from the perspective of an outside observer, information never actually crosses the event horizon. It gets smeared and thermalized on the surface, eventually leaking out via Hawking radiation. However, from the perspective of an astronaut foolish enough to fall in, they would cross the horizon uneventfully with the information safely intact inside. Both stories are simultaneously true for their respective observers, and there is no contradiction because no single observer can ever have both perspectives to compare. It's a cosmic version of what you see depends on where you stand, taken to its most extreme logical conclusion. But this elegant solution, in turn, gave birth to another, perhaps even more violent paradox, the firewall paradox. If black hole complementarity is correct, it implies that the event horizon cannot be the smooth, empty region of space that general relativity predicts. For the information to be duplicated both on the horizon for the outside observer and inside for the falling astronaut, a fundamental quantum rule against cloning information would be violated. To avoid this, some theorists argue that the event horizon must actually be a searing wall of high-energy particles, an incandescent firewall that would instantly vaporize anything attempting to cross it. So, the peaceful journey into a black hole predicted by Einstein is replaced by a catastrophic encounter with a wall of fire. This is deeply unsatisfying to many, as it simply replaces one paradox with another, suggesting our understanding of spacetime itself breaks down at the horizon. The stakes in this debate could not be higher. Resolving the information paradox is not just about understanding black holes. It is the most promising path toward a theory of everything, a single framework that seamlessly unites gravity with quantum mechanics. The way information behaves in these extreme conditions is the ultimate test for any candidate theory, such as string theory or loop quantum gravity. The paradox forces us to question the most basic concepts of space, time, and information. It suggests that our classical intuition about the universe is profoundly incomplete, and that the true nature of reality, when probed at its limits, is far stranger and more interconnected than we ever dreamed. The humble fate of a bit of information falling into a black hole may well hold the key to unlocking the deepest secrets of the cosmos. Yet as we try to complete our cosmic inventory, we find ourselves facing a different kind of problem, not with what is in the universe, but with how fast the universe itself is growing. This brings us to a modern crisis in cosmology, a puzzle so persistent it has its own dramatic name, the Hubble tension. It all revolves around a single, crucial number known as the Hubble constant, which measures the current rate of the universe's expansion. For decades, astronomers have worked to pin down this number with ever greater precision. The shocking result of that quest is not a single, agreed-upon value, but two distinctly different answers that refuse to reconcile. It's as if two of the world's most accurate clocks, built by master craftsmen and tested in every conceivable way, are stubbornly ticking at different speeds, and no one can figure out why. The first method for measuring the Hubble constant takes us back to the very beginning, using the cosmic microwave background as our ultimate time capsule. Sophisticated space-based observatories like the Planck satellite have mapped the faint temperature fluctuations in this ancient light with incredible detail. By analyzing the patterns of these hot and cold spots, the seeds of all future galaxy clusters, cosmologists can run the cosmic film in reverse. They can input the ingredients of the early universe into our most trusted models of cosmology and calculate precisely how fast the universe should be expanding today. This method gives us a very firm prediction, a Hubble constant of about 67 kilometers per second per megaparsec. In simpler terms, this means that for every megaparsec of distance, a staggering 3.26 million light-years, a galaxy is moving away from us at 67 kilometers per second faster due to the expansion of space. This is a measurement rooted in the pristine physics of the infant cosmos, and it is exceptionally robust. Then we have the second method, which measures the expansion rate directly in our own cosmic backyard. This technique relies on building what astronomers call the cosmic distance ladder. The first rung of this ladder involves objects with a known intrinsic brightness, such as Cepheid variable stars. These are stars that pulse with a regularity that is directly tied to their true luminosity. By measuring their pulse rate, we know how bright they should be. By comparing that known brightness to how dim they appear in the sky, we can calculate their distance with remarkable accuracy. We then use these Cepheids to calibrate the next rung of the ladder, which includes even brighter mile markers called Type Ia supernova. These supernovae are the gold standard for measuring vast distances because they all explode with nearly the same peak brightness. By observing these standard candles in galaxies at ever greater distances, astronomers can measure how fast those galaxies are receding from us and thus calculate the Hubble constant directly. This local measurement consistently returns a higher value, around 73 kilometers per second per megaparsec. The difference seems small, only about 6, but the precision of the measurements means this gap is statistically significant and refuses to go away. This discrepancy is far more than a minor accounting error. It is a direct challenge to our standard model of cosmology, a framework known as lambda CDM that has been spectacularly successful at explaining everything from the abundance of light elements to the large-scale structure of the universe. The fact that the early and late universe seem to be telling us two different stories about the expansion rate suggests that our model, while incredibly powerful, might be missing a crucial ingredient. Could there be a new, unknown type of particle that flooded the early universe, subtly changing how we interpret the cosmic microwave background? Perhaps dark energy is not a constant after all, but an evolving force that has strengthened over time, throwing off our local measurements. Some have even speculated about exotic possibilities, like the idea that our region of the cosmos lies within a vast, underdense bubble, a cosmic void that is locally distorting the expansion rate we measure. Yet, before we rewrite the laws of physics, scientists are meticulously checking for more mundane explanations. The possibility of a systematic error, a subtle flaw in our measurement techniques, is taken extremely seriously. Could there be an unrecognized bias in how we measure the distances to Cepheid stars? Are our models of supernova explosions not quite as uniform as we assumed? Teams around the world are cross-checking their data, developing new methods using everything from gravitational waves to giant red stars as independent distance indicators. So far, however, these careful checks have only deepened the mystery, as the new methods often land in an uncomfortable middle ground or even reinforce one of the conflicting camps. The Hubble tension stands as a thrilling and unresolved frontier. It is a testament to the fact that even our most fundamental constants are not beyond questioning, and that the universe still has profound lessons to teach us about its true nature, if we are only precise and humble enough to listen. Now let's journey from the vast scales of cosmic expansion to a breathtaking wonder within our own solar system, a structure so geometrically perfect it seems almost artificial. High above the cloud tops of Saturn, centered directly on its north pole, churns one of the most stunning and puzzling meteorological features ever discovered, a massive, persistent hexagon. This isn't a trick of light or shadow. It's a six-sided jet stream, a highway of wind racing around the planet's pole, with each side longer than the diameter of Earth. What makes this feature so extraordinary is its mind-boggling longevity and stability. It was first observed by the Voyager spacecraft flybys in the early 1980s, and decades later, when the Cassini spacecraft arrived for a long-term study of the Saturnian system, the hexagon was still there, unchanged. For over 40 years, through what would be multiple seasons on Saturn, this colossal geometric storm has held its shape, a perfect polygon etched onto a gaseous giant. The scale of this phenomenon is almost impossible to grasp. Each side of the hexagon stretches about 13,800 kilometers, and the entire structure rotates with a period of about 10 hours and 39 minutes, acting like a fixed, rigid body despite being made of nothing but swirling gas. Inside its boundaries, the weather is chaotic, with smaller vortices spinning and colliding, yet the hexagonal boundary itself remains sharp and unwavering. This presents a profound puzzle. On Earth, our atmospheric patterns are messy and transient. Hurricanes form and dissipate in days, and even the Great Red Spot on Jupiter, while centuries old, is a simple, albeit massive, oval. Saturn's hexagon is a different class of phenomenon altogether, a long-lived, precise geometric form emerging spontaneously from the turbulent, fluid dynamics of a planetary atmosphere. It defies our intuitive expectation that nature, especially on such a grand and chaotic scale, should favor curves and randomness, not sharp 60-degree corners. Scientists fascinated by this enigma have turned to the laboratory to try and crack the code. Using large cylinders of fluid, they simulate the conditions at Saturn's pole by spinning the container rapidly. When the fluid inside is set into motion, something remarkable happens. Under the right conditions, specific rates of rotation and differences in fluid speed between the center and the edges, the circular flow spontaneously breaks up into a stable set of regular polygons. Researchers have created not just hexagons but pentagons, octagons, and even squares simply by adjusting the spin. This suggests that the hexagon is a natural, if rare, outcome of fluid dynamics in a rapidly rotating system. It's an example of what physicists call a standing wave, a stable pattern that emerges from the complex interplay of forces, much like a specific note can create a standing wave pattern on a vibrating drumhead. In Saturn's case, the planet's deep atmosphere acts as the fluid, and its rapid rotation provides the energy to lock this wave into place. So, if we can recreate it in a lab, is the mystery solved? Not quite. While laboratory experiments show us that such shapes are possible, translating a small-scale model to a planet 10 times the size of Earth, with an atmosphere comprised primarily of hydrogen and helium and subject to immense internal pressures and heat flows, is an enormous challenge. The key question that remains is, what specific conditions on Saturn act to select and maintain a six-sided shape with such tenacity? The leading theory involves something called beta drift and the variation of the Coriolis effect with latitude. As you move from the equator to the pole on a spinning planet, the effective strength of the planet's rotation changes. This gradient can trap atmospheric waves and pin them at specific latitudes, allowing a polygonal pattern to form. The hexagon appears to be a manifestation of a particularly stable type of Rossby wave, a giant meander in the high-altitude wind currents that has become locked into a rigid, six-sided pattern. The incredible depth of Saturn's atmosphere, which may extend thousands of kilometers downward, likely provides a vast reservoir of energy that helps to stabilize this pattern against disruptions, allowing it to persist for decades and possibly even centuries. The enduring presence of the Saturn hexagon is a beautiful reminder that the laws of physics can produce artistry that rivals our most precise geometric designs. It stands as a testament to the complex, often hidden, order that can arise from apparent chaos. This isn't a static structure like a crystal. It is a dynamic, living pattern, a dance of winds and waves on a planetary scale. While we have a good theoretical framework for how it might work, the hexagon continues to challenge our detailed understanding of planetary atmospheres, pushing our models to their limits. It serves as a humbling and spectacular example of how much we still have to learn about the worlds right here in our own celestial neighborhood, where a simple, six-sided figure holds secrets to the fluid dynamics that may shape weather on planets throughout the galaxy. While our solar system holds its own geometric wonders like Saturn's hexagon, sometimes the most profound mysteries come to us as visitors from the depths of interstellar space. No object has embodied this idea more powerfully than the one known as Oumuamua. In October 2017, astronomers at the University of Hawaii's Pan-STARRS telescope detected a faint point of light moving across the sky. At first, it appeared to be just another asteroid or comet from our own solar system, but as they tracked its trajectory, they realized something extraordinary. This object was moving far too fast to be bound by the sun's gravity, and its path was unmistakably hyperbolic, meaning it was not orbiting the sun at all, it was just passing through. This was the first confirmed interstellar object ever observed within our solar system, a cosmic traveler from a star system far beyond our own, and it was given a name, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The initial excitement over its origin was quickly eclipsed by a cascade of truly bizarre physical characteristics. First, there was its shape. As astronomers monitored its brightness, they saw it pulse dramatically, growing much brighter and then much fainter in a regular cycle. The most plausible explanation for this extreme variation was that Oumuamua was tumbling end over end, and it was not a round or lumpy rock. The data suggested it was profoundly elongated, shaped like a cigar or a pancake, with its length estimated to be up to 10 times greater than its width. In a universe where most asteroids and comets are roughly spherical or potato-shaped, this was an oddity. We had never seen a natural object with such an extreme proportions. Then came the second, and perhaps more significant, anomaly. As Oumuamua sped away from the sun after its close approach, astronomers carefully plotted its trajectory against the predictable curve dictated by gravity alone. They found a clear discrepancy. The object was ever so slightly, but definitely accelerating. It was speeding up in a way that could not be explained by the gravitational pull of the sun or the planets. For a comet, this would be expected. As a comet heats up near the sun, its ice turns to gas, jetting out and acting like a natural rocket engine, giving it a non-gravitational push. But Oumuamua showed no signs of this activity. When scientists pointed their most powerful telescopes at it, they saw no coma. The fuzzy envelope of gas and dust that surrounds a comet's nucleus, and no tail of debris streaming behind it. It appeared as a completely inert, barren rock, yet something was pushing it. The scientific community was captivated, and the hunt for an explanation began in earnest. The leading natural theory proposed that Oumuamua was in fact a comet after all, but an exotic one. Perhaps it was a hydrogen iceberg. The idea was that in the cold, dense cores of giant molecular clouds, much of an object could be composed of solid molecular hydrogen. As this iceberg approached the Sun, the heat would cause the solid hydrogen to sublimate directly into gas, providing the thrust for the acceleration. Because hydrogen gas is invisible to our telescopes, this would explain the non-gravitational acceleration without a visible coma. However, this theory faced immense challenges. The interstellar space is bathed in cosmic radiation, and a hydrogen iceberg would likely have been eroded away completely long before it reached our solar system. Another natural explanation posited that Oumuamua could be a fractal-like aggregate of dust, a sort of cosmic dust bunny with such low density that light alone from the Sun could have given it the observed push, an effect known as radiation pressure. But the required density was so low that many questioned whether such a fragile object could have survived its long journey. It was this perfect storm of strangeness, the interstellar origin, the extreme shape, and the unexplained acceleration without a visible cause, that led to the most famous and controversial hypothesis. In a paper, Harvard astronomers S.H. Bealey and Avi Loeb explored the possibility that the acceleration could be explained by solar radiation pressure alone. For that to work, Oumuamua would need to be incredibly thin and lightweight for its size, possessing a large surface area but very little mass. The object that fit this description, they noted, was a light sail, an artificial structure designed to be pushed through space by the momentum of photons from stars, a technology humanity is only just beginning to develop. They suggested that Oumuamua could be a piece of a discarded light sail, a derelict from a technologically advanced civilization drifting through the galaxy. Professor Loeb famously argued that we should consider the possibility that it was an artifact, a piece of alien technology, perhaps even a defunct probe. This was not a claim made lightly, but an attempt to follow the scientific data to its most logical, if extraordinary, conclusion. The alien light sail theory ignited a firestorm of public imagination and scientific debate. While captivating, the vast majority of the scientific community maintains that an extraterrestrial explanation should be the absolute last resort, only after all natural possibilities have been exhausted. Critics pointed out that the available data on Oumuamua was sparse and limited. We only had a few weeks of observations before it became too faint to study. We never got a clear picture of it. Its true nature remains an unsolved puzzle precisely because it was a fleeting visitor, here and then gone forever, leaving behind only a trail of tantalizing clues. The legacy of Oumuamua is not a definitive answer, but a profound shift in perspective. It forced us to acknowledge that our solar system is not an isolated island, but is constantly being visited by material from other stars. It demonstrated that the universe is capable of producing objects that defy our easy categorization, and it underscored the critical importance of being ready for the next interstellar visitor. Because of Oumuamua, new projects and telescopes are being planned with the explicit goal of finding and studying these interstellar nomads, ensuring that the next time a messenger from afar arrives, we will be ready to unravel its secrets with more than just a hurried goodbye. Far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, lies a sprawling junkyard of icy remnants left over from the planet-forming process. This is the Kuiper Belt, a vast donut-shaped region populated by frozen worlds, some large like Pluto, and countless smaller chunks of rock and ice. For years, astronomers have been meticulously mapping this distant territory, and they have uncovered something deeply puzzling. As they count the number of objects at increasing distances from the Sun, the population grows steadily, just as our models of solar system formation predict. But then, at a specific boundary roughly 50 astronomical units from the Sun, 10 being the distance from Earth to the Sun, the bottom drops out. The number of Kuiper Belt objects doesn't just level off, it undergoes a catastrophic plunge. This dramatic and sudden scarcity is known as the Kuiper Cliff, and it presents a glaring problem. Our most trusted theories suggest the reservoir of icy bodies should continue or even increase for hundreds of astronomical units. Instead, we find a stark and unexpected edge to our cosmic backyard, as if a cosmic gardener came along and neatly trimmed the solar system's outer lawn. So, what could have carved out this precipitous drop in the distant ice? One of the most compelling and tantalizing theories is that the Kuiper Cliff is the gravitational signature of a hidden world, a massive planet whose presence we can only infer from the eerie emptiness it has created. This hypothetical object is often referred to as Planet 9. The idea is that a planet several times the mass of Earth, on a long and eccentric orbit far beyond the Kuiper belt, could be shepherding the smaller icy bodies. Through its immense gravitational influence over millions of years, this unseen giant would have either flung the objects in that region into the outer darkness, hurled them inward toward the sun, or ejected them from the solar system entirely. The result would be a cleared-out zone, a gravitational cliff that marks the boundary of its dominant sway. The very emptiness of this region becomes the most powerful clue to the planet's existence, a shadow cast by an unseen king on a distant, dark throne. However, the Planet 9 hypothesis, while elegant, is not the only possible explanation for this cosmic void. Another fascinating possibility takes us back to the very beginning of the solar system, over 4.5 billion years ago. Our system formed from a spinning, flattened disk of gas and dust called the protoplanetary disk. It's possible that this primordial disk itself had a sharp outer edge, perhaps truncated by a close stellar encounter with a sibling star in the Sun's birth cluster, or simply because it ran out of material at that specific radius. In this scenario, the Kuiper Cliff isn't a feature that was carved out later. It is a frozen fossil, a relic of the original construction site. The icy bodies we see today in the Kuiper belt would simply be the material that formed within that limited disk, and the cliff represents the original, fundamental boundary of the planetary construction zone. The solar system, in this view, was simply born with a defined edge. Each of these theories carries its own set of implications and challenges. The search for Planet 9 is a monumental astronomical endeavor, requiring some of the world's most powerful telescopes to scan enormous swaths of the sky for a faint, slow-moving dot. Its discovery would be a monumental event, rewriting our solar system's family portrait and explaining not just the Kuiper Cliff, but several other orbital oddities observed in the distant belt. On the other hand, if the cliff is indeed a primordial feature, it forces us to revise our understanding of how protoplanetary disks evolve and interact with their stellar environments. It suggests that our solar system's formation was a more isolated or distinctly shaped event than we previously thought. The Kuiper Cliff stands as a silent, distant sentinel, guarding the secrets of our solar system's formation and its possible hidden inhabitants, challenging us to look deeper into the darkness and question what we think we know about the space we call home. But our cosmic accounting problems are not limited to the grand scales of dark matter or missing baryons. They extend all the way down to the very building blocks of creation, to a fundamental flaw in our story of the universe's first moments. This is the cosmological lithium problem, and it is a paradox written in the ancient light of the oldest stars. In the first few minutes after the Big Bang, the universe was a seething, dense furnace of particles, hot enough for nuclear fusion to occur on a cosmic scale. This brief period, known as Big Bang nucleosynthesis, forged the universe's first atomic nuclei, primarily hydrogen, a good amount of helium, and trace amounts of the next lightest elements, lithium and deuterium. For decades, our calculations of the nuclear physics that govern this primordial forge have been incredibly precise. We can plug in the known densities of the universe and the strengths of the fundamental forces, and our models predict with stunning accuracy the amounts of deuterium and helium we should see in the oldest celestial objects. These predictions match the observations almost perfectly, but there is one glaring, persistent exception: lithium. The models are very specific. They tell us that for every 10 billion atoms of hydrogen in the universe, there should be about 5 atoms of the lithium-7 isotope. This is not a lot, but it should be a consistent, universal tracer of the Big Bang. However, when astronomers point their telescopes at the most ancient stars in our galaxy stellar relics that formed from nearly pristine material in the early universe, they consistently measure a lithium abundance that is only about 1/3 of what is predicted. These ancient suns contain only 1 or 2 lithium atoms for every 10 billion hydrogen atoms. This might seem like a tiny discrepancy, but in the precise world of cosmology, where our models of the Big Bang are considered one of the most successful theories in all of science, a factor of 3 error for a fundamental element is a monumental problem. It means that something is seriously wrong, either with our understanding of the nuclear reactions in the infant universe, or with the subsequent life cycle of this element in the ancient stars we use as our cosmic probes. So, where did the lithium go, or was it never made in the expected quantities to begin with? Scientists have been wrestling with this puzzle for decades, and the proposed solutions branch into 2 very different directions. The first possibility is that our understanding of stellar physics is incomplete. The oldest stars, known as population Roman II stars, are the benchmarks for these measurements. What if these stars are not the pristine time capsules we believe them to be? One theory suggests that over their billions of years of life, these stars could have been slowly dragging their surface lithium down into their hotter interiors, where it would be destroyed in nuclear reactions. This process, known as atomic diffusion or gravitational settling, could deplete the surface layers of lithium, making the star appear to have less than it was born with. Another stellar idea involves the possibility of pre-stellar nuclear burning. Before a star officially ignites and settles onto the main sequence, it goes through a hot, contracting phase. During this brief, violent birth, the protostar's core might become hot enough to fuse and destroy a portion of its original lithium, effectively erasing the primordial signature before the star even began its long life. The second and far more radical set of solutions looks back to the Big Bang itself and proposes that our standard model of particle physics is missing a piece. Perhaps an unknown type of particle was present in the early universe that interacted with the nuclear soup and altered the outcome. One compelling candidate is a theoretical particle known as a supersymmetric particle or a sparticle. In some models, these particles would have been unstable and decayed in the first few minutes, injecting extra energy into the primordial plasma. This extra energy would have increased the rate of nuclear reactions, potentially destroying the delicate lithium-7 nuclei as fast as they formed, or converting them into other elements like beryllium or helium. Another exotic proposal involves the idea of relic particles from the Big Bang known as negatively charged massive particles or CHAMP. If these existed, they could have formed unusual atoms with the primordial nuclei, fundamentally changing how they interacted and fused, thereby throwing off our careful predictions. These are not wild guesses, they are serious, mathematically rigorous attempts to solve the lithium problem by extending our understanding of the fundamental constituents of reality. The lithium problem is a beautiful and frustrating example of a cosmological anomaly. It is not a vague inconsistency, but a precise, quantitative disagreement between theory and observation. It forces us to question 2 of the most successful pillars of modern physics, our model of stellar evolution and our model of the early universe. It reminds us that even our most cherished and well-tested theories can have cracks, and that these cracks are often the very places where new discoveries are made. Whether the ultimate solution lies in a better understanding of the turbulent interiors of ancient stars or in the discovery of a new particle from the dawn of time, resolving the lithium problem will undoubtedly lead us to a deeper and more complete picture of our cosmic origins. It is a small number with very large implications, a faint whisper from the first 3 minutes of everything that challenges the story we tell about our own creation. Now, let's shift our focus from the grand architecture of the cosmos to the tiny, hypercharged messengers that scream through the void, carrying with them energies of almost unimaginable ferocity. These are ultra-high-energy cosmic rays, and to call them mere particles feels like a profound understatement. Imagine a single subatomic particle, a proton or the nucleus of an atom, traveling through space at nearly the speed of light, but carrying with it the kinetic energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. This isn't science fiction, these are real events. When one of these cosmic bullets slams into the upper atmosphere, it unleashes a chaotic cascade of billions of secondary particles, a sprawling air shower that can spread over dozens of square kilometers on the ground. The energy packed into that one primary particle is millions of times greater than what our most advanced human-made machine, the Large Hadron Collider, can produce. These are the most energetic particles ever observed in nature, and their very existence pushes the boundaries of what we believe is physically possible. The central puzzle surrounding these cosmic rays isn't just their immense power, but the profound mystery of their origin. According to a well-established limit in physics known as the GZK cutoff, named for physicists Greisen, Zatsepin, and Kuzmin, particles with such ludicrous energy should not be able to travel very far across the universe. Here's why space is not completely empty. It is filled with the faint relic radiation of the Big Bang, the cosmic microwave background. For an ultra-high-energy proton traveling across millions of light years, this background radiation is like a pervasive, thin fog. Each interaction with a photon from this fog is a chance for the proton to lose a significant fraction of its energy, a process akin to a high-speed bullet constantly smacking into a fine mist of gravel. Over immense intergalactic distances, this relentless ping-pong of interactions should sap the energy of any cosmic ray above a certain threshold, effectively creating a cosmic horizon, a distance limit beyond which we should never detect such powerful particles. The fact that we do detect them means they cannot have come from the far reaches of the universe. They must originate from within our own local cosmic neighborhood, within a sphere of about 150 to 200 million light-years, a region that, in cosmological terms, is practically our own backyard. This is where the mystery deepens into a full-blown cosmic detective story. If these ultra-high-energy cosmic rays are local, then the universe must contain natural accelerators of unimaginable power within our galactic vicinity, engines capable of firing particles to energies we can barely comprehend. The search for these cosmic engines has led scientists to consider some of the most violent and extreme objects known to astrophysics. One prime suspect is the active galactic nucleus, the supermassive black hole at the heart of a galaxy, where matter falling inward is torn apart and accelerated along powerful magnetic fields, potentially launching particles to near light speeds. Another candidate is the shock waves from colossal galaxy collisions, where vast regions of plasma and magnetic fields could act like a natural synchrotron, boosting particles over enormous distances. Gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, are also on the list, as their relativistic jets could potentially be the source of these rare and powerful projectiles. Yet, despite decades of searching with massive and ingenious observatories like the Pierre Auger Observatory in Argentina or the Telescope Array in Utah, a conclusive smoking gun has remained elusive. These detectors don't observe the primary particle directly. Instead, they cover vast areas of land to capture the sprawling secondary shower of particles it creates. By studying the pattern and timing of this shower's arrival at thousands of separate sensors, scientists can work backward to estimate the original particle's energy and, crucially, its direction of travel. However, here lies the final, frustrating twist. Cosmic rays are charged particles, and as such, their paths are bent and scrambled by the magnetic fields that permeate our galaxy and intergalactic space. By the time one of these ultra-high-energy particles reaches us, its trajectory is no longer a straight line pointing back to its source. It's like trying to trace the path of a ricocheting bullet in a hall of mirrors. The original direction is hopelessly lost. This magnetic scrambling means that even when we detect one of these phenomenal events, we are often left with only a vague, blurry smudge on the sky, a general region where the source might lurk, but no specific celestial object to blame. The hunt continues, a testament to the universe's ability to generate unimaginable power in the smallest of packages, while still masterfully concealing the colossal engines that give them birth. Amidst the unimaginably vast cosmic web of galaxies and clusters, there exists a region of space so profoundly empty, so staggeringly barren, that it has earned the haunting nickname the Great Nothing. This is the Boötes Void, a spherical chasm in the universe located in the constellation of Boötes, and its scale is almost impossible to comprehend. Imagine a region of space 330 million light-years across. To put that in perspective, if you placed our entire Milky Way galaxy inside it, with its 100,000 light-year diameter, it would be a mere speck, a single grain of sand in the middle of an empty sphere larger than the entire continent of North America. This void is not just a slightly underpopulated neighborhood. It is a true cosmic desert, a vacuum on a scale that defies our expectations of how matter should be distributed throughout the cosmos. The existence of such a colossal emptiness presents a direct challenge to our most successful models of the universe's large-scale structure. The prevailing lambda-cold dark matter model, which so accurately predicts the cosmic web of filaments and clusters we observe, also suggests that matter should be distributed with a certain degree of uniformity. While the model allows for voids to form, the sheer size of the Boötes void pushes the limits of statistical probability. It is an outlier of such magnitude that cosmologists have spent decades trying to understand how gravity, working over billions of years, could have possibly scooped out so much matter from one single region, leaving behind a volume of space that contains only a few dozen galaxies where our models would predict thousands. It's as if you walked into a forest that covered an entire continent, only to find one massive, perfectly circular clearing where almost no trees grew at all. This isn't just a curious oddity, it's a potential crack in our understanding of how the cosmic web was woven together. So, what does lie within this immense nothingness? It is not a perfect, absolute vacuum, which is a crucial part of the mystery. Early surveys, which first revealed the void in the 1980s, found it to be almost completely dark. However, more sensitive observations have since managed to identify a handful of galaxies drifting in this vast emptiness, like isolated ships on an endless, dark ocean. These galaxies are fascinating in their own right. They are often referred to as void galaxies, and they evolve in an environment completely unlike our own. Isolated from the crowded, violent interactions of galaxy clusters, these lonely islands of stars may represent a purer, more isolated form of galactic evolution, evolving slowly and quietly without the frequent mergers and gravitational harassment that shape galaxies in denser regions. Studying them offers a unique glimpse into how a galaxy's environment dictates its life story, providing a control sample for understanding the more common, cluster-bound galaxies like our own. How could such a void have formed in the first place? Scientists have proposed several compelling theories. One leading idea is that the Boötes void is the result of the merger of several smaller voids. In the early universe, as slight density fluctuations were amplified by gravity, small under-dense regions would have naturally formed. Over cosmic time, these smaller bubbles could have expanded and eventually run into each other, their boundaries merging to create one single gigantic void. Think of it like soap bubbles in a sink, where several smaller bubbles coalesce into one enormous one. Another, more speculative theory involves the influence of dark energy. As the universe expands, dark energy exerts a repulsive force that pushes galaxies apart. It's possible that in a region that was already slightly underdense, dark energy's effect was amplified, acting to accelerate the expansion of that local volume of space and effectively inflating the void to its current mind-boggling proportions. The Boötes void, therefore, might not just be a relic of the past, but an active structure whose continued growth is being driven by the same mysterious force that governs the fate of the entire cosmos. Ultimately, the Great Nothing is far more than an empty space. It is a critical laboratory for testing our theories of cosmology and structure formation. Its very existence forces us to question whether our standard model needs adjustment, or if we have simply witnessed an incredibly rare but statistically possible fluctuation in the density of the primordial universe. By mapping its precise boundaries and counting every single galaxy within it, astronomers are conducting a cosmic census that helps to calibrate our entire understanding of the distribution of both visible and dark matter. The Boötes void stands as a solemn monument to the fact that the universe is capable of extremes we are only beginning to map, a breathtaking expanse of nothing that, paradoxically, holds some of the most significant clues to understanding the everything that surrounds it. Now, if you thought the vast cosmic voids and high-energy particles were strange, consider a mystery unfolding on the infinitesimally small scale of the atomic nucleus, one that challenges the very rules that hold matter together. We are venturing into the world of the tetraneutron, a hypothetical and deeply controversial particle that, if it truly exists, would rewrite the textbooks on nuclear physics. Picture the nucleus of an atom, a tight bundle of protons and neutrons. The force that glues these particles together, the strong nuclear force, is a delicate balancing act. It powerfully attracts protons to neutrons and neutrons to each other, but it relies on the presence of protons to create a stable structure. For decades, the fundamental rule has been that you cannot have a nucleus made only of neutrons. Without protons to provide the necessary binding glue, a cluster of neutrons should simply fly apart in an instant. The idea of a bound state of two neutrons, a dynatron, has been searched for and never found. So, the notion of four neutrons magically clinging together seems to defy the laws of physics as we know them. It would be like trying to build a stable arch out of identical, smooth stones with no mortar. According to all our engineering principles, it should immediately collapse. The first tantalizing hints of this impossibility emerged from a particle accelerator in France in 2002. Researchers were firing a beam of stable helium isotopes into a thin target of another helium isotope. The goal was to study nuclear reactions, but the results contained a shocking anomaly. The data suggested that for a fleeting moment, a system of four neutrons had been created before immediately disintegrating. The signal was subtle, a specific signature in the energy and angles of the leftover particles that pointed toward a transient, unified state of four neutrons. This was not a direct observation, but a ghost in the data, an echo of something that should not be. The physics community was immediately skeptical, as well they should be. The finding was so revolutionary that it demanded extraordinary evidence. Many argued that what the team had seen was not a true bound particle, but merely a temporary resonant state, where the four neutrons happened to pass very close to each other for a minuscule fraction of a second before inevitably flying apart, giving the illusion of a single entity. The pursuit of the tetraneutron has since intensified, becoming a holy grail in experimental nuclear physics. Just a few years ago, a Japanese team employed a different, more direct approach. They used a beam of helium-8, a highly unstable, neutron-rich isotope, and directed it at a target of regular helium-4. In the resulting collision, the calculations suggested that the helium-8 nucleus could have shed its four neutrons in one single coherent unit. The properties of the debris were, once again, consistent with the formation of a tetraneutron that lived for just 1 × 10⁻⁻22 seconds. a span of time so short it is essentially immeasurable, but long enough in the quantum world to suggest a brief, bound existence. This newer evidence added weight to the case, but the central question remained: is this a genuine new form of matter, or are we being fooled by a complex and fleeting coincidence? The theoretical debate over this question is fierce and lies at the heart of the mystery. If the tetraneutron is confirmed as a true, albeit short-lived, bound state, it would mean that our understanding of the strong nuclear force is incomplete. The models that have successfully described nuclear interactions for nearly a century would need a significant revision. Theorists have scrambled to propose how such a particle could be possible. Some suggest it might be held together not by the standard strong force, but by a different mechanism altogether. One fascinating idea is that the four neutrons could form a baryonian state. This is a unique quantum arrangement where the system is bound as a whole, even though no smaller subset of particles within it is stable. Named after the baryonian rings, three interlocked rings that fall apart if any one is removed, a baryonian tetraneutron would mean that while pairs or trios of the neutrons cannot bind, the unique quantum correlations between all four of them create just enough net attraction to form a temporary, cohesive unit. It's a delicate and beautiful quantum dance that exists only when all the right partners are present. The implications of discovering such a particle would ripple far beyond a single laboratory finding. It would provide a completely new testing ground for our theories of nuclear structure, offering insights into the most neutron-rich matter in the universe. This has direct consequences for understanding the properties of neutron stars, those incredibly dense corpses of massive stars that are essentially giant atomic nuclei. The intense pressure inside a neutron star squeezes matter into states we cannot recreate on Earth, and the forces at play between pure neutrons are a key part of the equation. Confirming the tetraneutron would give us a vital data point, a tiny glimpse into the behavior of matter under such extreme conditions. It would help astrophysicists build more accurate models of how neutron stars behave, how they merge in colossal explosions that create gravitational waves and heavy elements like gold, and what their precise internal structure might be. The hunt is far from over. Reproducing the experiment and achieving a definitive, unambiguous signal is the next great challenge. Laboratories around the world are designing new experiments with more sensitive detectors and more powerful accelerators, all aimed at trapping this ghost. They are looking for a clear signature that can distinguish a true tetraneutron from a mere random clustering of neutrons. The story of the tetraneutron is a powerful example of how science progresses at the very edge of knowledge. It shows us that even the most established rules are open to question, and that the universe in its smallest corners might still be hiding forms of matter that defy our simplest expectations, waiting for the right experiment to reveal their fleeting, beautiful existence. For centuries, while most of humanity saw a silent, unchanging celestial companion, a handful of keen-eyed observers noticed something different. They reported seeing fleeting flashes of light, strange patches of color, and temporary veils of haze or obscuration on the surface of the moon. These brief, enigmatic events are known as transient lunar phenomena, or TLP, and they represent one of the oldest and most persistent mysteries in observational astronomy. Unlike the slow, predictable cycles of lunar phases, TLPs are unpredictable and ephemeral, appearing without warning and vanishing just as quickly, leaving behind only the testimony of those who witnessed them. The historical record is rich with these accounts. As far back as the 12th century, the English monk Gervase of Canterbury wrote of a flaming torch on the moon, and in the 18th century, the renowned astronomer Sir William Herschel observed what he described as red glowing points of light, which he speculated might be evidence of lunar volcanoes. These are not the musings of amateurs. They are detailed records from some of the most respected figures in the history of science, all pointing to a moon that is not entirely geologically dead, but one that occasionally stirs with subtle, unexplained activity. So, what could be causing these ghostly lunar flickers? Scientists have proposed several compelling natural explanations, each accounting for some of the observed events, but no single theory has yet managed to explain them all. One of the leading hypotheses involves outgassing. The moon's interior is not completely inert. It contains trace amounts of radioactive elements like uranium and thorium. As these elements decay, they produce heat and can release trapped gases, including radon. If a subsurface pocket of this gas finds a weak spot in the lunar crust, a fissure or a crack can burst through to the vacuum of the surface in a sudden, explosive release. This plume of gas and fine dust catching the sunlight could easily appear from Earth as a temporary brightening or a localized haze, obscuring the terrain below for a short period before dissipating into space. This idea gained significant support when the Lunar Prospector Orbiter in the late 1990s actually detected elevated levels of radon gas emanation from several regions that were also historical hotspots for TLP reports, providing a compelling link between theory and observation. Another, more frequent and easily demonstrable cause is the relentless bombardment of the lunar surface by meteoroids. Without an atmosphere to protect it, the moon is constantly being pelted by space debris, ranging from tiny specks of dust to larger rocks. When one of these projectiles strikes the lunar surface at speeds of tens of kilometers per second, the kinetic energy of the impact is instantaneously converted into heat and light, creating a brilliant flash that can be visible from Earth with a modest telescope. These impact flashes are now regularly recorded by dedicated observation programs, and they account for a significant number of the short-duration, point-like flashes reported over the years. However, while impacts explain the sudden, brilliant flashes, they don't as easily account for the longer-lasting glows or the diffuse hazes that have been described, events that can persist for minutes or even hours. This is where other, more subtle physical processes come into play. The lunar surface is a world dominated by electrostatics. During the 2-week-long lunar day, the surface is bathed in intense ultraviolet radiation from the sun, which knocks electrons loose from the dust grains. This can cause the fine, abrasive lunar soil or regolith to become electrically charged. In certain conditions, this built-up electrostatic charge could suddenly discharge, leaping from grain to grain or even creating a faint, glowing plasma near prominent features like crater rims. This could manifest as a brief, shimmering glow or a subtle change in the local albedo or reflectivity of the surface. Another fascinating possibility is that of space weathering in real time. The moon's surface is constantly being altered by solar wind and micrometeorite impacts. A fresh impact, even a small one, could expose underlying material that has a different color or composition, or it could trigger a small-scale avalanche of darker or brighter soil down a steep slope, creating a temporary color change or a dark smudge that would be visible from Earth until the relentless solar radiation darkens it back to the prevailing gray. Despite these plausible mechanisms, the mystery of transient lunar phenomena endures because the evidence remains frustratingly anecdotal and difficult to verify. The events are so transient and unpredictable that they are nearly impossible to study with large, scheduled observatories. Furthermore, Earth's own turbulent atmosphere can create visual illusions and distortions that mimic the appearance of a TLP. A momentary ripple in the air can make a bright crater rim appear to shimmer or flash, leading to a false positive. This has led to a healthy skepticism within the scientific community. However, the sheer volume of consistent reports from experienced observers, often clustering around specific geological features like the crater Aristarchus, a region known for its geologically young and reflective material, suggests that there is a real, physical phenomenon at work. The puzzle of TLPs is a classic example of a scientific frontier where careful, patient observation must eventually be married with sustained, targeted monitoring from lunar orbit or even from surface stations to finally separate lunar fact from terrestrial fiction, revealing the last faint whispers of activity from our seemingly silent neighbor. From the haunting silence of the Boötes void to the fleeting possibility of a tetraneutron, we've explored mysteries spanning the vast and the infinitesimal. Now we turn our attention to a different kind of enigma, one that radiates from the very heart of our cosmic home, a mysterious, persistent glow that has turned our galactic center into a beacon of high-energy light. This is the galactic center excess, an unexplained surplus of gamma-ray radiation that bathes the core of the Milky Way in an energy that our best models cannot fully account for. When scientists using NASA's Fermi Gamma-Ray Space Telescope meticulously mapped the sky in gamma rays, they expected to see a certain level of background radiation from known processes. What they found, however, was a robust and significant overabundance of these high-energy photons emanating from a region around the galactic center, a glow that is far more intense than the sum of its recognized parts. So, what are these recognized parts that are coming up short? The center of our galaxy is a tumultuous and crowded place, teeming with potential gamma-ray sources. Cosmic rays, high-speed protons, and atomic nuclei constantly slam into clouds of interstellar gas, and these violent collisions produce gamma rays. We also have pulsars, the rapidly spinning corpses of massive stars, which act like cosmic lighthouses, sweeping beams of radiation across space, including high-energy gamma rays. When you add up the expected contributions from all these known sources, the total falls significantly short of the intense, diffuse glow we actually observe. This leftover signal, this excess, forms a roughly spherical halo of gamma-ray light centered on the Milky Way's core. It's not a collection of distinct points, but a pervasive, fog-like emission that defies a simple, conventional explanation, suggesting that something else, something unseen, is at work in the most crowded neighborhood of our galaxy. This is where the mystery takes a thrilling turn into the realm of the hypothetical. The leading and most controversial explanation for this excess is that we are witnessing the ghostly signature of dark matter itself. The theory hinges on a fascinating possibility. If dark matter is made of a new kind of particle, as most physicists suspect, then it's possible that these particles are their own antimatter counterparts. Wherever dark matter is densely concentrated, these particles could occasionally collide and annihilate each other upon contact. The galactic center is precisely such a place. Our models tell us it should be packed with an immense halo of dark matter, providing the perfect environment for these annihilations to occur. When two of these theoretical particles meet, they would convert their mass directly into energy, following Einstein's famous equation, erupting in a flash that produces, among other things, gamma rays. The specific energy spectrum and the spatial distribution of the galactic center excess align remarkably well with what some models predict for the annihilation of dark matter particles with a specific mass, making this an incredibly compelling, albeit unproven, interpretation. It offers the breathtaking possibility that we are not just inferring dark matter's presence through gravity, but are finally seeing its direct, radiant aftermath. But before we rewrite the laws of physics, scientists have been diligently exploring other, less exotic possibilities. The primary challenger to the dark matter interpretation is the idea that the excess is not a smooth glow from annihilations, but is actually composed of thousands of individual, point-like sources that are simply too faint for the Fermi telescope to resolve individually. The prime suspects in this scenario are millisecond pulsars. These are ancient neutron stars that have been recycled by siphoning material from a companion star, a process that spins them up to incredible rotational speeds, causing them to emit powerful beams of gamma radiation. The galactic center is an old stellar environment, exactly the kind of place you would expect to find a large population of these faint, rapidly spinning objects. If they are there in sufficient numbers, their collective, unresolved light could perfectly mimic the smooth, diffuse glow we attribute to the excess. It's like looking at a city from a great distance at night. You don't see the individual streetlights, but their combined effect creates a pervasive haze of light that defines the city's outline. The central debate, therefore, boils down to a cosmic census. Is the glow a true fog from dark matter annihilations, or is it the combined starlight from a vast, unseen metropolis of dead stars? The scientific battle to resolve this question is ongoing and fierce, a testament to how difficult it is to decipher signals from such a complex and distant environment. To distinguish between a smooth dark matter signal and a collection of point sources, astronomers have employed sophisticated statistical analyses, looking for telltale clumpiness in the gamma-ray emission that would betray the presence of individual pulsars. Some studies have claimed to find evidence for such an underlying point source population, strengthening the millisecond pulsar case. Others, however, argue that the emission remains statistically smooth and that there simply aren't enough other indicators like radio waves to support the vast number of pulsars required. The resolution likely lies in the future, with more sensitive gamma-ray telescopes or new observations in other wavelengths like radio that could finally pinpoint the faint pulsars hiding within the glow. The galactic center excess stands as a brilliant puzzle at the crossroads of particle physics and astronomy. It is either our first direct glimpse of the universe's most elusive substance, or a powerful reminder of the vibrant, hidden stellar activity thriving in the chaotic core of our galaxy, a luminous mystery that continues to illuminate the frontier of our understanding. But to truly appreciate the ghostly presence of dark matter that seems to permeate the cosmos, we need to understand the single, most pivotal observation that first revealed its existence, an observation so fundamental it literally reshaped our entire understanding of gravity on the largest scales. This brings us to the perplexing behavior of galaxies themselves, and a discovery that began with the meticulous work of an astronomer who refused to accept the easy answer. The story centers on a deceptively simple question: how do stars and gas clouds move within a galaxy? We might assume that a spiral galaxy, with its brilliant, dense core and sweeping, sparser arms, would behave much like our own solar system. In our solar system, the planets orbit the Sun according to the elegant rules laid down by Johannes Kepler and explained by Isaac Newton's law of gravity. The key principle here is that the vast majority of the mass is concentrated in the center, the Sun. As you move outward, the gravitational pull weakens dramatically. This is why Mercury, the innermost planet, zips around the Sun at a blistering 47 kilometers per second, while distant, icy Pluto plods along at a leisurely 5 kilometers per second. The speed of an orbiting body drops off predictably with distance in a very specific relationship known as a Keplerian decline. Now apply that logic to a galaxy like our Milky Way. If a galaxy were just a collection of stars, gas, and dust, if all its mass were in the visible material we can see, then the stars in the crowded central bulge should orbit very quickly, while the stars in the outer spiral arms, far from the gravitational center, should be moving much more slowly. They are like Pluto, far from the central pull of the Sun. For decades, this is exactly what astronomers expected to find. But when they began to measure the actual orbital speeds of stars and hydrogen gas clouds in other spiral galaxies, they were met with a result that defied all expectations. The data revealed something astonishing and, at first, deeply confusing. Instead of the orbital speeds dropping off in that predictable Keplerian fashion as they moved further from the galactic center, the speeds remained high. They flattened out. Stars and gas clouds on the very outskirts of these galaxies, in the faint, tenuous outer regions, were hurtling around just as fast as the stars closer to the bright core. It was as if every planet in our solar system, from Mercury to Pluto, orbited at the same breakneck speed, a scenario that would instantly tear our solar system apart under the known laws of physics. This bizarre and persistent pattern, graphically represented, is known as a flat rotation curve, and it became one of the most significant anomalies in 20th century astronomy. The astronomer who provided the most compelling and robust evidence for this phenomenon was Vera Rubin, working with Kent Ford in the 1970s and 80s. Using sophisticated spectrographs, they meticulously measured the rotation of the Andromeda galaxy, our nearest large galactic neighbor. By analyzing the Doppler shift of light from stars and gas at different distances from the center, seeing how the light was stretched or compressed as the material moved toward or away from us, they could map out the galaxy's rotation speed with unprecedented precision. Their results were unequivocal and revolutionary. The outer regions of Andromeda were not obeying the rules. This was not a glitch or an error. It was a fundamental feature of how spiral galaxies work. The only possible explanation was that there had to be a tremendous amount of unseen mass surrounding the galaxy, mass that was not concentrated in the center but was distributed in a massive, invisible sphere or halo that extended far beyond the visible edge of the galaxy itself. This invisible mass provided the extra gravitational grip needed to whip the outer stars around at such high speeds, preventing them from flying off into the emptiness of intergalactic space. Without this hidden anchor, the galaxies would simply not hold together. This discovery of flat rotation curves provided the first direct and undeniable evidence for what we now call dark matter. The dark in its name is perfectly literal. This matter does not emit, absorb, or reflect any form of light. It is completely transparent, utterly invisible to our telescopes across the entire electromagnetic spectrum. We cannot see it, but we can feel its gravitational influence as surely as we feel the Earth's pull. The rotation curves told us that every spiral galaxy is like an iceberg. The glittering stars and glowing gas we see are merely the tip, while a vast, deep foundation of dark matter lies beneath, providing the structural integrity for the entire system. The sheer scale of this dark halo is staggering. For a typical spiral galaxy, the visible disk of stars might be 100,000 light-years across, but the dark matter halo that envelops it can extend for well over 1,000,000 light-years, a tenfold increase in size, containing far more mass than all the stars, gas, and planets combined. This galactic revelation is not an isolated curiosity. It is a universal truth. Every single spiral galaxy that has been studied with sufficient care exhibits this same behavior. The flat rotation curve is a universal signature, a cosmic rule that applies from the smallest dwarf galaxies to the largest spirals. This consistency is what makes it one of the strongest pillars of evidence for dark matter's existence. It's not just one or two odd galaxies, it's a fundamental aspect of galactic architecture. The dark matter halo acts as a cosmic skeleton, a framework upon which the ordinary matter can condense and form the beautiful structures we see. In fact, computer simulations of the universe's evolution show that without this dark matter scaffolding, the gas in the early universe would not have clumped together efficiently enough to form galaxies in the first place. The gravity of dark matter provided the initial seeds, the gathering points, that allowed the ordinary matter to fall in and eventually light up as stars. The rotation curves are more than just evidence of a hidden mass. They are a glimpse into the very process of cosmic construction, revealing the invisible hand that shaped the luminous universe we observe today. The profound implication of this is that what we see when we gaze at a magnificent spiral galaxy in a telescope is only a tiny fraction of what is actually there. We are witnessing the light show, but we are missing the vast, silent, and mysterious engine of gravity that makes the show possible. This discovery fundamentally humbled us, forcing a dramatic revision of our place in the cosmos. We are not just made of the rare, visible stuff. We are embedded in a much larger, unseen reality that dominates the gravitational landscape of the universe. The flat rotation curve, first glimpsed in the careful data of pioneering astronomers, remains one of the most clear-cut and powerful arguments that the universe is filled with a mysterious substance that interacts with us only through the force of gravity, a ghostly presence that holds the galaxies together and whose true nature continues to be one of the greatest quests in modern science. Yet this very limit, this cosmic speed bump for particles, appears to be not quite as absolute as we once thought. This brings us to the deeply puzzling case of the GZK cutoff suppression. To understand this mystery, you first have to picture the journey of an ultra-high-energy cosmic ray. Let's say a proton with an almost unimaginable amount of energy is shot out from an active galaxy billions of light years away. As it travels through the vast emptiness of intergalactic space, it is not alone. The universe is filled with the faint, cold glow of the cosmic microwave background, the leftover heat from the Big Bang. For this high-flying proton, that gentle background radiation is anything but harmless. Each photon from the CMB, though weak, is like a tiny piece of gravel. When our proton, moving at over 99.9% the speed of light, smacks into one of these CMB photons, something dramatic happens. The collision is so violent that it can create new particles, specifically a particle called a pion. This process, known as the GZK effect, acts like a cosmic toll booth, robbing the proton of a significant chunk of its energy with every single interaction. Over a long enough distance, this relentless ping-pong of collisions should drain the energy of any cosmic ray from a distant source down to a level below a specific threshold, a point known as the GZK cutoff. It should create a cosmic horizon, a distance beyond which we simply cannot see such ultra-high-energy particles. But here's the twist that has left physicists scratching their heads. Our detectors on Earth do, in fact, record a number of these ultra-high-energy events. The puzzle isn't that we see them, but that we seem to see too many of them, or rather, we see particles whose energies seem to defy the expected level of suppression. The data from observatories like the Pierre Auger Observatory show a distinct drop in the number of cosmic rays at the very highest energies, which is good. That's the GZK cutoff at work. However, the shape of that drop-off, the precise way the number of particles declines with energy, doesn't perfectly match the theoretical predictions. There appears to be a subtle suppression of the cutoff itself. The expected sharp cliff in the data looks more like a softened, gentler slope. It's as if a significant number of these ultra-high-energy particles are finding a way to sneak past the cosmic toll booth, arriving at Earth with energies that, according to our best models, they should have lost billions of years ago. This anomaly forces us to consider two radically different possibilities, each with profound implications. The first and more conservative explanation is that our map of the local universe is incomplete. The GZK horizon for these particles is about 150 million light-years. Within that relatively local volume of space, there must be cosmic accelerators of unimaginable power capable of producing these particles. Perhaps we have simply not yet identified all the nearby sources, like hidden active galactic nuclei or unusually powerful gamma-ray bursts, that are responsible for this flux. Maybe the magnetic fields that scramble the paths of these charged particles are stronger or weaker than we think in our local galactic neighborhood, focusing more of these high-energy events toward us than our models anticipate. In this scenario, the suppression of the GZK cutoff is an astronomical problem, a call to conduct a better census of the colossal engines lurking in our cosmic backyard. The second and far more thrilling possibility is that we are seeing the first hints of physics beyond our current understanding. The standard model of particle physics, which has been spectacularly successful, might be missing a chapter. What if a new, unknown type of particle is involved? Some theorists have proposed that these ultra-high-energy events are not caused by protons at all, but by a more exotic, stable particle that does not feel the GZK effect in the same way. A candidate like a super-heavy, stable particle from the early universe, often called a WIMPzilla, could travel vast distances without being slowed down by the CMB, easily bypassing the cutoff that constrains ordinary protons. Another radical idea involves modifications to Einstein's special theory of relativity. There are speculative frameworks that suggest the very nature of space-time might change at these extreme energies, subtly altering how particles interact with the CMB photons and allowing them to travel further than our standard equations permit. The observed suppression could be a tiny crack in the foundation of modern physics, a signal that the laws of nature are slightly different at energies 1,000,000 times greater than what our most powerful colliders can produce. The quest to solve this mystery is a race against statistical uncertainty. Detecting these ultra-high-energy cosmic rays is a game of patience. A single square kilometer on Earth might be struck by one only once per century. Observatories need to cover immense areas to gather enough of these rare events to map the cutoff with high precision. Every new detection is a precious data point. The path forward involves not just collecting more data, but also cross-referencing the arrival directions of these particles with deeper and more complete maps of the nearby universe, searching for correlations with known astrophysical objects. At the same time, theorists are refining their models, exploring every conceivable nuance of particle interactions and cosmic magnetic fields. The GZK cutoff suppression is a classic example of a frontier mystery, where a small discrepancy in the data holds the potential to either simply refine our astronomical catalogs or to completely revolutionize our understanding of the fundamental laws that govern the cosmos. But just as we confront the high-energy frontier of cosmic rays, we find that the universe's capacity for wonder extends to structures of breathtaking symmetry and elegance. Far from the chaotic violence of galactic centers, there exists a celestial artwork of such precise geometry it seems almost crafted by design. This is the Red Rectangle Nebula, a planetary nebula located about 2,300 light-years away in the constellation Monoceros. The name itself barely does it justice, for what the Hubble Space Telescope revealed was not a simple rectangle, but a stunningly complex and layered structure. At its heart lies a brilliant, hot binary star system, and surrounding it is a series of concentric, rectangular rungs of glowing red gas and dust, all connected by luminous spikes that form a perfect, startling X-shape. It looks less like a typical cosmic cloud and more like a vast, luminous ladder or an intricate piece of cosmic stained glass, its sharp corners and straight lines standing in stark defiance of the rounded, billowing forms we expect from dying stars. This remarkable geometry is what makes the red rectangle such a compelling anomaly. Most planetary nebulae are formed when a dying, sun-like star sheds its outer layers, puffing them out into space in often beautiful but chaotic and asymmetrical bubbles and rings. The forces at play, intense stellar winds, radiation pressure, and magnetic fields typically create ethereal, flowing shapes like the Helix Nebula or the Cat's Eye Nebula. The red rectangle breaks this mold completely. Its concentric squares and crisp X-shape suggest a formation process governed by an unusually high degree of order and constraint, a kind of cosmic physics that favors sharp angles over soft curves. The leading theory to explain this unique architecture focuses on the dynamics of the central binary star system. Here, two stars are locked in a close orbital dance. As one of them reached the end of its life and expanded into a red giant, it began to spill its material onto its smaller companion. This transfer of mass wasn't a smooth, continuous flow, but rather a series of violent, episodic outbursts. Think of it not as a steady exhale, but as a succession of precise, powerful coughs, each ejecting a shell of gas and dust into the surrounding void. However, these outbursts alone wouldn't create the iconic rectangular shape. The missing piece of the puzzle is a thick, dense torus, a donut-shaped ring of dust and gas that encircles the binary pair right at their equatorial plane. This torus acts like a cosmic corset, squeezing the outward flow of material. When the stars eject gas, it tries to expand in all directions, but it finds its path blocked along the equator by this dense belt. The only direction it can easily go is upward and downward, away from the restrictive waistline, funneling the material into two opposing cones. From our vantage point, we are looking at this bipolar flow almost directly from the side. The edges of these two cones appear to us as the long, straight lines of the X, while the concentric rectangles are actually the rims of individual gas shells, ejected in separate outbursts over time, like ripples frozen in a cosmic pond. The brilliant red color that gives the nebula its name comes from a special type of emission. The ultraviolet light from the hot, central stars is causing complex carbon molecules, known as polycyclic aromatic hydrocarbons, to fluoresce, painting the entire structure in a deep crimson glow. Despite this elegant model, the red rectangle has not surrendered all of its secrets. The exact mechanism that creates such perfectly straight lines and sharp corners, as opposed to the more typical curved lobes of other bipolar nebulae, is still a subject of active research. Some scientists speculate that magnetic fields anchored to the orbiting stars and the dust torus could be helping to collimate or narrow the outflowing jets into such razor-sharp edges. Others are investigating the precise properties of the dust grains themselves, wondering if their size and composition in this particular system are uniquely suited to creating such a well-defined structure. Furthermore, the central star system itself is enigmatic. It is what's known as a post-AGB star, a brief and poorly understood evolutionary phase that occurs just before a star becomes a white dwarf. The specific conditions during this short-lived period might be the key to unlocking why this system, among thousands, produced such a geometric marvel. The Red Rectangle Nebula, therefore, is more than just a pretty picture. It is a unique laboratory for studying the final, dramatic breaths of stars, a place where the complex interplay of binary orbits, mass transfer, and constrained outflows writes its signature on the sky in a language of perfect angles and radiant red light, a temporary monument to the hidden order that can underlie even the most turbulent cosmic deaths. So, after grappling with the immense power of these particles and the frustrating blur of their paths, we arrive at an even deeper layer of this mystery. For a long time, it was assumed that if we couldn't pinpoint individual sources, these ultra-high-energy cosmic rays should at least arrive from every direction in the sky equally, like a perfectly uniform, invisible rain. This isotropic distribution would make sense if their sources were evenly sprinkled throughout the nearby universe, or if the scrambling by magnetic fields was so complete that all directional information was utterly erased. But the universe, it seems, despises perfect symmetry. When scientists at the world's largest cosmic ray observatories, like the Pierre Auger Observatory, finally accumulated enough of these rare events to draw a statistical map of their origins, they saw something extraordinary. It wasn't a random scatter of dots. Instead, there was a slight but undeniable clustering, a subtle tendency for these cosmic bullets to arrive more frequently from certain patches of the sky than from others. This deviation from perfect uniformity is what scientists call an anisotropy, and its detection was a monumental breakthrough, a faint signal emerging from the noise that whispered, "The sources are not everywhere." Mapping this anisotropy is a task of almost superhuman patience. Imagine trying to map the pattern of rainfall during a drought by collecting individual drops in buckets scattered across a continent. Each detection of an ultra-high-energy cosmic ray is that precious, singular drop. The observatories that perform this work are engineering marvels. The Pierre Auger Observatory, for instance, covers 3,000 square kilometers of Argentinian prairie, an area larger than some small countries, with 1,600 separate water tank detectors spaced over a mile apart. When a cosmic ray strikes the atmosphere, the resulting cascade of particles, known as an air shower, spreads out and triggers these tanks. By noting the precise nanosecond that each tank is hit, scientists can reconstruct the angle of the original particle's arrival with remarkable accuracy. But to see the pattern, the anisotropy, you need not dozens, not hundreds, but thousands of these events, collected over more than a decade of continuous 24/7 observation. It is a triumph of big data and international collaboration, a slow, meticulous process of building up a cosmic picture, one impossibly energetic particle at a time. The patterns that have emerged are both tantalizing and deeply perplexing. The most significant anisotropy discovered so far is not a sharp, bright point that screams "source here," but rather a broad, diffuse excess, a region in the sky towards the constellation Centaurus where these ultra-high-energy events appear to be about 6% more common than the average. While 6% might not sound like much in the world of high-energy astrophysics, where statistical significance is everything, this is a major detection. It's a clear signal that the sources of these particles are not randomly distributed. There is a lopsidedness to the universe's most powerful accelerators. This broad hotspot intriguingly points towards a region of the sky that is rich with potential cosmic engines, including the general direction of the nearby Centaurus, a galaxy, a giant active galaxy with a supermassive black hole at its heart, and the broader Virgo supercluster, the massive congregation of galaxies that our own Milky Way belongs to. It's as if our cosmic map has a giant, faint arrow painted on it, pointing towards a crowded celestial metropolis and saying, "Look over there, yet here lies the final, exquisite frustration." Even with this map in hand, identifying the specific culprit or culprits remains fiendishly difficult, and the reason brings us back to those pesky galactic and intergalactic magnetic fields. These fields, though incredibly weak, trillions of times weaker than a common refrigerator magnet, permeate the vast spaces between galaxies. A proton carrying such an enormous electric charge, screaming across millions of light years, does not travel in a straight line. It gets deflected, its path bent into a gentle, chaotic curve. The amount of this bending depends on the particle's energy and the strength of the magnetic fields it traverses, fields that we have only a very rough map of. For the highest energy cosmic rays, the deflection might be a few degrees, but over intergalactic distances, a few degrees translates to a potential error on the sky larger than the full moon. So that broad hotspot we see is not a photograph of the source region. It's a smeared-out, blurry fingerprint. The true source of these particles could be anywhere within that large, fuzzy patch. We have a neighborhood, but we are still searching for the exact address. This means the hunt has now become a multi-messenger endeavor. Astronomers are taking that blurred anisotropy map and cross-referencing it with every other type of observation they have. They are scouring that region of the sky with radio telescopes, X-ray observatories, and gamma-ray telescopes, looking for any object that seems unusually powerful or violent. They are asking if the arrival of a particularly high-energy cosmic ray coincides with a flare from a distant black hole or a merger of neutron stars detected by gravitational wave observatories. It is a cosmic triangulation effort, using every tool at our disposal to narrow down the possibilities within that tantalizing, fuzzy hotspot. The ultimate goal is to one day see multiple messengers, a gravitational wave signal, a flash of gamma rays, and a cluster of ultra-high-energy cosmic rays, all originating from the same tiny point in the sky, finally revealing the identity of one of the universe's ultimate power plants. The cosmic ray anisotropy is therefore a critical stepping stone. It is the universe giving us our first real directional clue in a decades-long detective story, a faint but statistically robust pattern in the rain that tells us we are on the right trail, even if the final destination still lies shrouded in magnetic mist. And this brings us to our final, and perhaps most immediate, cosmic mystery, one that has vaulted from the fringes of science fiction to the halls of government and into the heart of our cultural conversation. We are talking about unidentified aerial phenomena, or UAP. For decades, the very topic was taboo in serious circles, often dismissed as misidentification, secret military tests, or simple fantasy. But the landscape has shifted dramatically. In recent years, official government reports, declassified military videos, and sworn testimony from highly trained pilots have forced a profound and public reckoning. We now have a formal admission from authorities that objects are operating in our skies and in our oceans with performance characteristics that defy our current understanding of physics. They display instantaneous acceleration, hypersonic velocities without sonic booms, and the ability to move seamlessly between air and water, all with no visible means of propulsion or control surfaces. These are not vague lights in the distance. They are objects tracked by the world's most advanced radar and targeting systems, witnessed by experts with the highest possible credibility. The crucial and responsible perspective, championed by intelligence agencies and scientific bodies alike, is that the overwhelming majority of these incidents will inevitably have prosaic explanations. Many will turn out to be advanced drones from rival nations, next-generation military prototypes whose existence is classified, sophisticated atmospheric balloons, or simply rare but known natural phenomena like ball lightning or ice crystals that can create bizarre optical illusions on sensor systems. The process of investigation is one of rigorous elimination, and for most cases, a conventional answer will eventually be found. This is the most likely and most cautious approach to the data. However, the core of the mystery lies in what's left over. After you've filtered out all the identifiable aircraft, the weather phenomena, and the sensor glitches, a small, stubborn residue of cases remains. These are the incidents with multiple sensor correlations, objects seen simultaneously by radar, infrared cameras, and the naked eye, that exhibit that handful of truly extraordinary characteristics. It is this tiny, unexplained fraction that forces us to widen the aperture of possibility and ask a question that resonates with every other mystery we've explored: what if? This is where the topic of UAPs connects directly to our cosmic voyage. For centuries, humanity has gazed at the stars and wondered if we are alone, confronting the profound silence of the Fermi Paradox. We've searched for biosignatures in exoplanet atmospheres and listened for radio signals from distant civilizations, all while operating under the assumption that any contact would be across light years of emptiness. But the UAP mystery presents a radically different and far more provocative hypothesis. What if the answer to "where is everybody" isn't out there in the distant void but has been here all along, operating just beyond the edge of our perception? The idea that even a minuscule percentage of these unexplained objects could represent technology of non-human origin is perhaps the most astounding possibility one can entertain. It suggests that a civilization or multiple civilizations have not only arisen elsewhere but have mastered the fabric of space-time in ways we can barely imagine. The physics-defying maneuvers described by pilots, sudden right angle, turns at thousands of miles per hour, descent from the edge of space to sea level in seconds, would require a command over inertia and gravity that is the stuff of our most advanced theoretical physics papers. Concepts like warp drives, which manipulate space-time itself to achieve faster-than-light travel, or metamaterials that can render an object invisible, move from pure speculation into the realm of potential engineering. If these objects are real and are what they appear to be, then they are not just flying machines. They are living proof that the cosmic challenges we've discussed, dark energy, higher dimensions, the nature of reality, are not just academic puzzles but are solvable. They would be a physical demonstration that a technology millions of years more advanced than our own would be, as Arthur C. Clarke famously said, indistinguishable from magic. Consider the implications of this through the lens of our other mysteries. The vast distances of space, which seem like an impenetrable barrier to us, might be traversable through means we haven't yet discovered. The dark energy that is accelerating the expansion of the universe could be a potential power source. The strange quantum entanglement of particles could be the basis for instantaneous communication across interstellar space. A civilization that has cracked these codes would not see the cosmos as a collection of isolated islands, but as an accessible, interconnected network. Their presence here would not necessarily require a generation ship traveling for millennia. It could be as simple as stepping through a door we haven't yet found the key to. This line of thinking also offers a potential and deeply humbling resolution to the Fermi Paradox, the zoo hypothesis we discussed earlier, the idea that advanced civilizations are aware of us but are observing without interference, would take on a new, tangible meaning. Their operations would be deliberately designed to be just ambiguous enough to avoid definitive confirmation, allowing our civilization to develop naturally until we reach a certain maturity, perhaps a point where we begin to understand the fundamental nature of the universe ourselves. Ultimately, whether the UAP enigma is resolved as secret human technology, a breathtaking new natural phenomenon, or something even more profound, its true value may lie in the questions it forces us to ask. It is a mirror held up to our own ignorance and our own potential. It challenges the arrogance of assuming we understand everything about our world and our place in the cosmos. Just as the discovery of the cosmic microwave background revolutionized our view of the universe's birth, and the observation of dark energy reshaped our understanding of its fate, the serious investigation of UAPs has the potential to revolutionize our understanding of life and intelligence in the universe. It connects the grand billion light-year scale of cosmic mysteries to the intimate, immediate reality of our own planet. It suggests that the final frontier might not be thousands of light years away, but is instead hovering in the thin, fragile layer of atmosphere that separates us from the void, a constant, silent reminder that the universe is far stranger and far more wonderful than we have ever allowed ourselves to believe. And so our journey ends not with a final answer, but with a profound appreciation for the questions themselves. We have traveled from the incomprehensibly large, where dark energy silently scripts the universe's final fate and dark matter weaves the invisible cosmic web, down to the bafflingly small, where the rules of quantum mechanics and gravity clash within the abyss of a black hole. We have witnessed stars that flicker as if obscured by alien megastructures, felt the ghostly pull of the Great Attractor, and stood before the stark geometric perfection of Saturn's hexagon. We have chased interstellar interlopers like Oumuamua, listened for cosmic screams in fast radio bursts, and confronted the haunting silence of the Fermi Paradox. From the missing lithium in ancient stars to the inexplicable glow at our galaxy's core, and from the cosmic rain of ultra-high-energy particles to the enduring whispers of lunar mysteries, each phenomenon is a brilliant thread in a tapestry of profound wonder. This grand tour of 25 cosmic enigmas reveals a universe that is not a static, solved puzzle, but a dynamic, living frontier, teeming with mysteries that challenge the very edges of our comprehension. These lingering questions are not signs of scientific failure. They are the very engines of discovery. Every unexplained anomaly, every stubborn piece of data that refuses to fit our existing models is a gift. It is an invitation to look deeper, to think more creatively, and to push the boundaries of our knowledge. The cosmological crisis of the Hubble tension forces us to question our most fundamental constants. The puzzle of the tetraneutron challenges the core rules that bind atomic nuclei. The search for the source of ultra-high-energy cosmic rays drives the creation of detectors that span entire continents. Each mystery is a catalyst, sparking new technologies, birthing new theories, and inspiring generations to peer into the unknown. The history of science is not a straight line of accumulating facts. It is a story of revolutions born from anomalies. What we cannot explain today is the foundation for the breakthroughs of tomorrow. Embracing the unknown is the most vital step toward true understanding, a testament to our species' unquenchable curiosity and our relentless drive to make sense of the magnificent cosmos we call home. So the next time you find yourself under a clear night sky, I invite you to look up with fresh eyes. See not just the pinpricks of light, but the vast, dynamic, and deeply mysterious cosmos they represent. See the invisible hand of dark matter shaping the galaxies, feel the silent pressure of dark energy accelerating the void, and wonder about the possibilities that might lie hidden in the quiet spaces between the stars. Our exploration has shown that the universe is far stranger, more complex, and more wonderfully bizarre than we ever imagined. And this journey is far from over. It is a story that we are all a part of, a collective human endeavor to unravel the secrets of existence. We want to hear which of these cosmic mysteries captured your imagination the most. Was it the unsettling idea of the Great Filter, the ghostly evidence for Planet 9, or the quantum conundrum of the black hole information paradox? Share your thoughts in the comments below, and let's continue this conversation, exploring the great unknown together.